Studying is states of matter, chemistry class 11. So here we study about the properties of gaseous state, particles in gaseous state, and also we study liquid state also. Okay, ma? In liquid state we study about viscosity, are able to understand, surface tension. These are the properties of the liquids in liquid state. Are able to understand, ma? So viscosity and surface tension already we study in physics. Okay, so same concepts you will study in liquid state in the case of states of matter also. So this one we will not discuss. I will discuss only about gaseous state in this topic, because same discussion we will do once again in mechanical properties of solids and fluids. We will study this topic. Okay, so therefore first of all we have to study what is meant by ideal gas. Okay, ma? So first of all we will write the properties of ideal gas, ma? Properties of ideal gas. Clear? So all the atoms or molecules are considered to be perfect spheres. Okay, ma? So this is the first property of an ideal gas. Okay. Second property is that they are always in random motion. Okay, ma? Always they will be present in random motion. Okay. Third property is that, okay, ma, they undergo only elastic collisions. Okay, ma? Fourth property is that the force of attraction or repulsion between the atoms or molecules is zero. Clear, no, ma? So they are point masses with zero volume. Okay, ma? So these are some of the properties of an ideal gas. Okay, and can you name any one ideal gas, ma? Can you name any ideal gas existing in this universe? Ideal gas ko example chapanda, huh? Hydrogen. Clear, ma? I am asking about inert, I am not asking about inert gases, I am asking about ideal gases. Clear, no? So ideal gases does not exist. Clear, ma? There is no gas which is called as ideal gas. Are you able to understand? Sima, for doing these calculations, we require some standard, no? Some standard of measurement should be there. So these properties we will consider to be standard properties, and we do all the calculations. Are you able to understand? Let us see, for example, some of the properties, ma? So all the atoms or molecules are considered to be perfect spheres. So every molecule, is it a perfect sphere? It is not perfect sphere, okay? But we take spherical shapes only, then we do the calculations. Then we get approximate values. Are you able to understand? Similarly, what is the second property? They are always in random motion, so this is always satisfied. All the particles, they will be moving in random motion, whether it is an ideal gas or whether it is a real gas. Are you able to understand? So they undergo elastic collisions. What is meant by elastic collisions? Already we studied, no, ma? When two atoms or molecules, when they collide, there is no loss of kinetic energy. Akka, namaskaram. Meekosame cheppandi. Are you able to understand, ma? So what is meant by elastic collision? When these collisions happen, there is no loss of kinetic energy. That's what we have studied in physics, no? Elastic collision means what? Momentum also should be conserved. Kinetic energy also should be conserved. But practically in real gases, this will never happen. But in ideal gases, we consider the cases of elastic collisions and we do the calculations. Understood, Dhamma? And we also assume that there is no force of attraction or repulsion in between these atoms or molecules. But in reality, there will be very slight force of attraction or repulsion existing between the real gases, between atoms of real gases. But in ideal gases, we consider forces to be zero and we do the calculations. Clear, Nama? So therefore, viscous forces, surface tension, all these are absent. Okay. Similarly, we consider all of them, they are point masses with zero volume. when compared to the size of the container, size of the atom or molecule is very small, no? Container size to compare cheste, atom size, molecule size, it will be very small. So therefore we consider they are very point masses and their volume is considered to be 0. So these are the properties which we study for ideal gases, and by taking these considerations we do the calculations. But point is that there is no ideal gas existing in this universe. Okay? All these are ideal means what? Exemplary gases. A gases should be like this. Ideal student ante evani 720 ki 720 వచ్చేవాడు ఐడియల్ స్టూడెంట్ అనమాట. 300 400 వచ్చేవాళ్ళంతా సూడో స్టూడెంట్స్. అట్లనే ఇది కూడా ఐడియల్ గ్యాసెస్. క్లియర్ నమ్మా? సో సెకండ్ పాయింట్ ఈస్ దట్ at very low pressures and high temperatures, okay ma, pressure should be very low and temperature should be very large, then real gases behave like ideal gases. Okay ma? So this is another important point which we have to study. Okay? So when pressures are very low and temperatures are very large, then all these properties which we have written here, they will be almost satisfied. Okay? So pressure ela undali very low and temperature should be very large. In that condition, all these properties will be obtained by a real gas. Then it starts behaving like an ideal gas. Are you able to understand? Make a note up to here. Okay. So see the next topic, we will study about a very important equation which is called as ideal gas equation. Ideal gas equation means what? This is the equation which will be followed by all the ideal gases. Or you can say this equation will be followed even by real gases also. But what is the condition? Temperature should be very large and pressure should be very small. Then even real gases also, they will behave like ideal gases. Okay ma? Now see. So what is the equation? PV is equals to nRT. This is the equation. This is the equation of an ideal gas. What is meant by P here? P is called as pressure. Okay ma? All these quantities you know, no need of explaining once again. V is called as volume. N is called what here? N is called as number of moles of a gas. And what is meant by mole already we studied, no ma? Avogadro number of atoms, molecules or ions is called as mole. Clear? So this gas is having how many moles? That is represented by N here. And what is meant by R here? R is called as universal gas constant. Clear ma? And what is its value? It is 8.31 joules per mole Kelvin in SI system. In CGS system, if you want to write it approximately 1.98 calories per mole Kelvin. So these are the values of R value. Okay ma? And how we have converted this 8.31 into 1.98 ma? We know that 1 calorie is equals to 4.2 joules, no? This value always you should remember ma. 1 calorie is equal to 4.2 joules. So therefore 1 joule is how much? 1 joule is equals to 1 by 4.2 calories. That's all. No? So here instead of 1 joule, I can substitute 1 by 4.2. Then automatically 8.31 converts into 1.98 calories per mole Kelvin. Are you able to understand ma? And what is meant by T here? T is called as temperature in Kelvin. Always you have to write Kelvin scale only ma. Clear? Temperature should be written in which scale? Kelvin scale only you have to write. But here you can make a note point. Note point is that, clear? So change in temperature of Celsius is equals to change in temperature in the case of Kelvin. Both are same. Okay? So what is the amount of change in temperature in Celsius scale? Same will be the amount of change in Kelvin scale also. What is the reason? Endukala? See ma, temperature in Celsius magnitude and temperature in Kelvin magnitude, they are not equal. But change wise they are same. Are you able to understand? Because if I rise 1 degree Celsius in Celsius, 1 degree Kelvin also will rise. Divisions are same. In Celsius and Kelvin, AV same, divisions are same. But temperatures are not same. The magnitudes are not same. For example, if I write 0 degree Celsius. Okay ma? So 0 degree Celsius is equals to how many Kelvin? 273 Kelvin. Okay? 1 degree Celsius is equals to 274 Kelvin. Okay ma? 274 Kelvin. Okay. So here what is the rise in Celsius? Delta C is how much? 1. Here delta K is how much? This is also 1. Changes are equal, but temperature magnitudes they are not equal. So you should remember. So wherever you get delta T, then you can write directly in Celsius or Kelvin, both are same. But where you have only T, then you have to write in Kelvin scale, you should not write in Celsius scale. Arthamavutundi kada difference? Make a note up to here. Okay, ma? So, this is the equation which is called as ideal gas equation. PV is equals to nRT. Now see ma. So, we have a constant which is called as Boltzmann constant. Okay. So, Boltzmann constant K is equals to 1.38 into 10 power minus 23 joule per Kelvin. This is the value of Boltzmann constant. Okay. And Boltzmann constant can also be written as R divided by Na also. Okay. Boltzmann constant K can be written as R by Na also. What is R? Universal gas constant. What is Na? Avogadro number. So R divided by Na is also called as K value. Okay. Now, so therefore instead of R what I can write? Instead of R I can write K into Na no ma? K into Na. So take this value and substitute in ideal gas equation. So PV is equals to N. Instead of R I can write K into Na multiplied by T. I can write like this, no? Okay. Now can you say what is meant by N here? Small n means what? Number of moles. Small n means number of moles. So how many methods are there to represent a number of moles, ma? Three. What are they? So mass divided by molecular mass. This is one method. Clear, no, ma? Total volume divided by volume of 1 mole of gas. Clear, no? At a standard temperature and pressure. Clear? One more method is total number of molecules, ions or atoms divided by Avogadro number of atoms, molecules or ions. So these are the three methods by which I can write number of moles. No? Okay. So therefore, N value, how I can write? N value can be written as number of moles multiplied by Na. Can I write like this? N is equals to number of moles divided by Na. But here in ideal gas equation I have small n, no? Instead of small n what I can write? N divided by Na. So take this value and substitute here. Okay. Then let us see what I will get. So PV is equals to, instead of small n I can write N divided by Na multiplied by K into Na multiplied by T. This is what I can write now. Okay. Now what are the terms which can get cancelled? Na get cancelled. So PV is equals to NKT. So this is another equation for ideal gas. Are you able to understand? Where here nRT means N is the value for number of moles. R is universal gas constant. But here PV is equals to capital NKT. Okay, ma? So capital N is called as number of atoms, molecules or ions. K is called as Boltzmann constant. Understood, no? So questions can be given on any of these equations. You should be careful about this. Make a note. Now see. So in ideal gas equation, PV is equal to nRT. We will write different cases which are possible. No? It means how we are heating the gas or how we are removing gas from the system. Okay, there are three methods. First one is that number of moles of a gas, it is a constant. Okay, ma? R is already a constant, no? And if I maintain temperature also to be constant, then it is what kind of process? If temperature is constant, this is isothermal process, no? Isothermal process. Okay. So number of moles is a constant, R is a constant, T is a constant. I am heating the gas in this method. Okay. Then I can say that if these three are constants, then I can write pressure into volume is also a constant, no? Because nRT, if they are constants, the product of nRT is a constant. So PV also will become a constant. So constant I will write by K, X, Y, anything. Okay. So therefore I can write if PV is a constant and if I remove this equation, then I can write that pressure is inversely proportional to volume number, or also I can write volume is inversely proportional to pressure. Are you able to understand? And this condition is exactly what is called as Boyle's law. This equation what we call, this condition is called Boyle's law. Okay. So therefore, what is the equation of Boyle's law? How can we write the equation? If number of moles also means that mass of the gas is also constant. No? Number of moles means amount of gas, quantity of gas. If number of moles are constant, what about mass of a gas? Mass of a gas is also a constant. So therefore, you can write mass also. Mass of the gas is also a constant. So when number of moles and temperature, when they are constant, then pressure of the gas is inversely proportional to volume. It means if you increase the volume, pressure will decrease. If you increase pressure, volume will decrease. They are inversely proportional to each other. and that law itself is called as Boyle's law. No need of writing the statement, I hope you can understand. Okay, ma? So therefore, I can write PV because this is a constant. I can write in different conditions, I can write P1 V1 is equals to P2 V2 is equals to P3 V3, and I can write for any number of conditions, and all of them they should be equal. Okay, because P into V is a constant. Understood now? Very simple. So therefore, in Boyle's law, we write relation between which one and which one? We write relation between pressure and volume. And which are the constants here? These are the constant. R is a constant. Number of moles is a constant. So therefore, mass of the gas is also a constant. Temperature also a constant. And this is definitely isothermal process because temperature is not changing. Understood now? So then we write case number 2. Okay, ma? So in case number 2, which one shall we keep constant? Let us take pressure to be a constant, clear ma? And number of moles of the gas to be a constant. If number of moles are constant, I can say mass of the gas is also a constant. Okay? And R is always a constant. So therefore, now which are the variables ma? Pressure is a constant, N is a constant, R is already a constant. Then which are the variables here? Volume is directly proportional to temperature. That's all, no? And this statement is nothing but, this is the case of which law? Chal's law. Or you can call it as Charles' law. Okay, ma? Or the same equation, you can call it as Charles' law of volume also. Okay, ma? Charles' law of volume also, you can call this one. Okay. So therefore, volume is directly proportional to temperature. In which conditions? When pressure, number of moles, if they are constant. If number of moles are constant, mass of the gas is definitely constant. Clear? So therefore, I can write V by T is a constant. And that constant I can call anything, K, X, Y, Z, anything. So therefore, V1 by T1 must be equal to V2 by T2 is equals to V3 by T3. And it goes on. And finally, it is equal to K. Okay, so V1, V2, V3 are different volumes at different temperatures of T1, T2 and T3. So whatever, how many conditions you can take, all of them, their ratio must remain constant. That is called as Charles' law. Okay, so then we are writing case number 3. Now which of them shall I take constant? I will take volume to be constant. Okay, how I am heating the gas? I am heating the gas such that I am not changing volume. How can I heat a gas without changing volume? Heat the gas in a closed container. Heating the gas in closed container, whatever may be the change in temperature, volume will never change, clear, like this. So volume is always a constant, and I can say that still what are the constants? Number of moles is a constant. Okay, ma? So therefore, mass of the gas is also a constant, and R is definitely a constant. Then which are the variables in this condition? Pressure and volume. So the pressure and temperature. So I can say that pressure is directly proportional to temperature. So if I start heating the gas, temperature increases, no? If temperature increases, pressure also increases. In which condition? If volume of the gas is remaining constant. Okay? So if volume remains a constant and pressure and temperature, they will increase as directly proportional. So what is the increase in temperature? So by using some constant, the change in pressure also will change. And what is that constant? That constant can be anything depend upon the initial volume of the gas, initial state of the gas. Clear? I can write P by T is a constant, and this constant can be anything, which is called as constant of proportionality. Okay? It depends on initial conditions of the gas. Okay, ma? So therefore, I will write P1 by T1 is equals to P2 by T2, and it goes on, and it is equal to K. So you can write like this also. Are able to understand, ma? So these are some of the cases which we have studied. Okay. So let us take one more case, ma? Case number 4. Okay. So in this case, I will take pressure to be constant. Okay, ma? Temperature also to be constant. Okay. Pressure I am taking constant, temperature I am taking constant. So therefore, if pressure and temperature are constant, then which are the variables we have? Volume and number of moles, they are variable. So volume is directly proportional to N. Are you able to understand, ma? And this law is called as, this case you can call. This case is called what? Avogadro's law. Okay, ma? Avogadro's law. So what is meant by Avogadro's law? if any sample of gas, it may be oxygen, it may be CO2, it may be helium, it may be hydrogen, any gas, if pressure and temperature, if they are maintained constant, then volume is directly proportional to number of moles of a gas. Or I can also say that pressure, temperature, volume, all of them if they are maintained constant, then any gas will have same number of moles. Okay? Or I can say pressure, temperature, volume if they are constant, any sample of gas should have same number of atoms, molecules or ions. I can say like this also. Are you able to understand more? So write down the statement of Avogadro's law, then we will try to understand what is meant by Avogadro's law. Okay? So different statements are there. I am writing one statement, statement of Avogadro's law. Very important statement, because if you don't understand this one, solving of problems will become problematic. Okay? Now see. So at same temperature, pressure and volume, okay, samples of any gas will have same number of atoms or molecules, or just you can call them as particles also. This law is called as Avogadro's law. Are you able to understand? Now let us try to understand what is the meaning of this statement which we have written. For example, so this is one container, this is another container, okay, so this is another container, okay. So volume of the gas is V1, volume of the second gas is V2, volume of the third gas is V3. And we are writing volumes, they are equal. V1 is equal to V2 is equal to V3. For example, 1 liter container, 1 liter container, this is also 1 liter container. Volumes are same, no? Clear, no? And pressures are also same. So pressure of this gas is P1, pressure of this gas is P2, pressure of this gas is P3. Temperatures are T1, T2 and T3. Then what, according to Avogadro's law, what I have to write? Pressures are also if they are equal. Clear, no? And temperatures also they are equal, no? So T1 is equal to T2 is equal to T3. Size is same, pressure is same, temperature also is same. Then in that condition, if this gas contains, let it be oxygen gas, let it be hydrogen gas, and let this one be CO2 gas, any gases you can take. Then this container, if it contains 100 molecules, this container also will have 100 molecules only. This container also will have 100 molecules only. This is called as Avogadro's law. Are you able to understand, ma? So what are the conditions? Pressure and temperature, if they are same, then volume is directly proportional to number of moles. Okay, ma? If volume increases, number of moles of the gas also increases. But if volume is also made constant, if volume is also constant, the number of moles also will remain constant. Number of moles is nothing but number of particles, no? Because 1 mole is a fixed value, no? If number of moles are constant, number of particles are also constant. Number of particles means what? Atoms or molecules or ions. Anything will be same. So this is the symbolic representation of Avogadro's law. Okay, ma? Volumes are same, pressures are same, temperatures are also same. Then whatever may be the gas, whether it is oxygen, whether it is hydrogen, whether it is carbon dioxide, helium, argon, neon, whatever may be the gas, they must have same number of atoms or same number of molecules. Understood, no? So this is a very, very, very important law. Clear? Because while solving these problems, we should have a very good idea of all these laws. Otherwise, problem solution will become very tough. Okay? So see, depending on the given question, you can select any one of these laws. Okay? So depending on the question, he may be asking question on Boyle's law, he may be asking question on Charles' law, he may be asking question on Avogadro's law. Are you able to understand? He may be asking question on Gay-Lussac's law. Gay-Lussac's law, did I write, ma? This law is nothing but Gay-Lussac's law. So write down here. Okay, ma? Case number 3 here we are writing out. This law is called as what? Gay-Lussac's law. Okay, ma? Or also you can call it as Charles' law of pressure also. Okay? Same Gay-Lussac's law, what you can call? You can call it as Charles' law of pressure also. Okay, ma? And this law is called as Charles' law of volume, no? And this is called Charles' law of pressure, or in modern terms we are calling this law as Gay-Lussac's law. Understood, no, ma? Okay. So you can use any one of these equations, ma, for solving problems depending upon the situation of the problem. Or you can do one thing. You can use the universal equation. What is the universal equation? PV is equal to nRT. So all these laws, they are derived from this law only, no? So this only you can use directly, without trying to find out whether it is Boyle's law, Charles' law, Gale's law, Talabadukokunda. You can use this equation and you can do the calculation. Because all of them, they are derived from only one equation, PV is equal to nRT. Understood, no? That's it. Okay, make a note. Sima. So we are following some strategies for solving problems. So first strategy is that, so for any problem which is given directly, you can use PV is equal to nRT without searching for whether it is Charles' law, Boyle's law, Avogadro's law. Directly you can use PV is equal to nRT. And second condition is that, if for example, if you are mixing gases, if you are removing some gases, you are heating the gases, you are compressing the gas, whatever you do, chemical reaction should not happen. Clear, Nama? If chemical reactions doesn't take place, the number of moles of any gas always remains a constant. Are you able to understand? For example, in a container, clear, ma? I am taking 2 moles of hydrogen gas, for example. Okay? 2 moles of hydrogen gas I am taking in a container. If I compress this gas, 2 moles, will it change, ma? 2 moles remains to be 2 moles only. Number of particles, they never change, no? Clear? Similarly, if I expand this one, if I increase its pressure, or even if I heat this gas also, nothing will change, no? 2 moles remains to be 2 moles only. But number of moles will change in which condition? Only when any chemical reaction changes, then delta Ng value we have to consider. What is meant by delta Ng? The change in number of moles of products minus number of moles of reactants in gaseous form. That is called as delta Ng. No? But as far as chemical reaction is not happening, number of initial moles of gas is equals to number of final moles of the same gas. Okay. So based on this technique, now we are going to solve some problems. Okay. Let us see this question, ma. So, a vessel of 120 ml capacity contains certain amount of gas at 35 degrees Celsius and 12 bar pressure. Okay, ma? So, the gas is transferred to another vessel of volume 180 ml at 35 degrees Celsius. Then what would be its pressure? Now, can you say, question is based on which law? Baga chudandi. Question is based on which law? What is the initial temperature? 35. Final temperature? 35. So temperature is not changing. It means relation is only between pressure and volume only. If relation is between pressure and volume, then what is that law? Boyle's law. Are you able to understand, ma? So therefore, if he is asking questions on Boyle's law, definitely you can write pressure is inversely proportional to volume. Okay, ma? Boyle's law. Okay. Then you can write P1 V1 is equals to P2 V2. That's all. 2 conditions are there, no? Okay. So what is the initial volume? Initial volume is V1. Clear, Nama? Initially what is happening actually? There is a gas present in 120 ml volume and we are shifting that gas to another container. Initially container was smaller. Then we have shifted the same gas to bigger container. It means volume has increased, no? If volume increases, what happens to pressure? Pressure should decrease. That's all. Nothing we are changing. So just we are shifting the gas from smaller container to bigger container. That's it. So what is its initial volume? It is 120 ml and total gas is shifted to 180 ml of gas. That's it. That's what we are doing. So temperature is not changed, no? So this is an isothermal process. And we cannot say isothermal process because we are not supplying any heat energy, no, here. Temperature is not changing, so therefore we can consider this one to be Boyle's law. Therefore, what is the initial pressure, ma? 12 bar. See, ma, here units are given in bars. Okay, but options are also given in bars only, no? So you need not convert this one into atmosphere or any other unit. Okay, should be very careful about units now. So answer is also given in bars only, no? You need not convert. So pressure is 12 bar and initial volume is 180 ml. Clear, Nama? And here you can write down 1 ml is equals to 1 centimeter cube. Both are same. 1 ml and 1 centimeter cube both are same. Okay, ma? And final volume is also given in ml only, no? Initial volume is given in ml. Final volume also in ml only. So again, you need not change the units here. So initial volume is 120. Okay, ma? P2. Final pressure is, that's what I have to find out. And what is the final volume? Final volume is 180. So therefore just do this calculation. So P2 is equals to 12 into 120 divided by 180. So if you do this calculation, then it is 12 into 12 divided by 80. Okay, ma? So, any mistake we have done? Na? Why we need not convert? No. Here also given in ml, here also given in ml only, no ma? Then maybe options may be wrong. Options may be wrong. We did not change the units. Pressure, it is given in bars. Volume, it is given in ml. So you need not convert anything. Even if you convert also, conversion factors will get cancelled with each other. No, you need not convert. Maybe options may be wrong. Clear, no? What was the initial pressure, ma? 12, no? So 0.8 may not be correct. 8 may be correct. Because slightly we are increasing the volume, no? So pressure also decreases slightly. It cannot become 0.8. No, options are wrong here. So do this calculation, how much you will get? 8, huh? So option is 8 bar. That is the option. Clear, no? So 8 bars. This is the final pressure. Understood, no? That's it. I don't think. Let us see. See here. So two glass bulbs A and B are connected by a very small tube having a wall. It means, let me draw this beautiful diagram. So this is one glass bulb. This is another glass bulb. Okay, ma? So both of them, they are connected by a tube. And to this tube, there is one valve also. Okay? Valve means what? If I rotate this valve, gases will intermix from one glass container to another glass container. That is called as a valve. Clear, no ma? So let this one be A, this one be B, and bulb A has how much volume? 100 centimeter cube. This is the volume of this one. While B is empty. On opening the valve, pressure falls down to 40%. Okay, ma? Then volume of the second bulb must be. Then volume of the second bulb is how much? That is the question. Clear, no ma? It means initially only glass A is filled with gas. And this one is empty here. Empty means there is no gas. Vacuum is present inside this one. If I open this valve, can you say what will happen? Gas will flow into this second container also, no? And see, a gas, wherever it sees the volume, it tries to occupy the total volume. Are you able to understand? So as soon as you release this one, some of the gas enters into second bulb also. Okay? And then what about pressures? Now gas will redistribute such that pressure in first bulb, pressure in second bulb will be same. Same pressure must be present. Are you able to understand, ma? Because temperatures are same, no? So pressure exerted by each gas also will be same. Okay? Now see. Therefore, what is the note point we have to write? A point is that, so as valve is opened, okay, ma? Gas in A will expand and occupy B also. Okay, ma? And final pressure in both containers, remains same. Okay? Why pressure remains the same? Because there is only single gas, no? So wherever it tries to find the volume, it tries to go there until all the pressure everywhere becomes same. Okay? So therefore finally I can say that final pressure in gas A, container A, is equals to final pressure in container B. Definitely pressures will be same, final pressures. PF means final pressure. Understood, Nama? So therefore, temperatures, are they changing, ma, here? Temperatures are not changing. Clear? But what is changing? Volume is changing. So therefore, pressure will change. So again, question is based on what? Again, question is still based on Boyle's law, not Charles' law. Okay? But now we don't go for discussion whether it is Boyle's law, Charles' law, Avogadro's law, all that. Just we will use the equation PV is equals to nRT, ideal gas equation. Okay, ma? Now see. So another note point is that chemical reaction, is it happening, ma? So if I just open this valve, so this gas goes and reacts with something here. Chemical reaction is not happening, no? Okay, so next point is that note point. Chemical reaction does not take place. Okay. So if chemical reaction doesn't take place, what is the point we have studied? Number of moles of initial gas and number of moles of final gas, they must be equal. So for example, initially here 100 molecules of this particular gas is there. Even after opening also, 100 molecules only present, but those molecules, they will be distributed both in A as well as in B also. So therefore, what I can write as chemical reactions are not happening, N initial is equal to N final. Total initial number of moles and total final number of moles, they must be equal, because number of molecules of gas, they are not changing. Are you able to understand? So therefore, N value, how I can write from this ideal gas equation? N is equal to, I can write PV divided by RT, no? PV divided by RT. So N1 is equal to N2. So write down P1 V1 divided by RT1 is equal to P2 V2 divided by RT2. Can I write like this or not? Right, sir? Definitely I can write. No? Number of moles are same. So number of moles formula PV by RT. So P1 V1 by RT1 is equals to P2 V2 by RT2. R is always a constant. So R value you can cancel. Temperature, he did not mention anything about temperature, no? Just if I open the gas, temperature, will it change? Temperature does not change. So temperature also is a constant. So again I got same Boyle's equation, P1 V1 is equals to P2 V2. So substitute there. Clear, Nama? So what is the initial pressure here? Where is that? He did not give anything about pressure, no? 40%, it falls down to 40%. That's what he gave, no? So let us call initial pressure is P. Let us consider initial pressure is P, because he did not give anything, so I am considering it to be P. And initial volume is how much? At least he gave that one. Where is that? 100 centimeter cube. So final volume is 100. Okay, initial volume. Divided by, there is nothing to divide. So this is equals to P2 V2. Final pressure. Final pressure is, it falls to 40, no? He did not say falls by 40, he did not say. He said pressure falls to 40. It means what is the final pressure? It is 40 by 100 multiplied by P. This is the final pressure. Can I write like this? Understood, Nama? Initial pressure is P. Final pressure is only 40% of initial pressure. So 40 by 100 multiplied by P. Now what is the total final volume? Can you see? Final volume. Initial volume, gas was present only in this container, Nama? Initially, where gas was present? Only in this container. Now gas is present in this also, in this also. Both containers it is present. No? So therefore, what is the final volume? Final volume I can write 100 plus V. Initial volume 100 only, no? 100. 100 plus V. This is how I can write. Understood, no? Initially, only this much volume of gas was present. But when I open the valve, now gas is entering into second one also, no? Its volume only he is asking us to find out, no? Find the volume must be dash. So final volume of this one, let it be V. Then what is the total volume? 100 plus V. Now gas is present in all the containers, no? So 100 plus V will become the final volume. Just calculate V value from that one. That is my required answer. Okay? So calculate. So where shall we calculate? Okay. So P and P get cancelled. So therefore 100 is equals to 40 by 100 multiplied by 100 plus V. That's all, Nama. PP get cancelled and remaining everything is present like it is. So 0, 0 get cancelled. So 1000 is equals to 400 plus V. 400 plus 4V. Clear, Nama? So therefore 4V is equals to 600. So V is equals to 600 by 4 is how much? 150. 150 centimeter cube is our answer. That's it. Understood, Nama? Very simple. So based on which logic we have done this calculation, ma? Logic is that there is no chemical reaction. Chemical reaction, if it doesn't change, number of moles of a gas remains constant. Initially if there are 2 moles, finally also 2 moles only. Okay? And we know ideal gas equation, no? Just substituting and we are getting the answer. In the Sima. So 2 closed vessels of equal volume containing air at pressure P1 and temperature T1 are connected to each other. Let us draw the diagram of this one, ma. So this is one container. Okay. So this is another container, ma. Volumes are same, no? Volume is V. Here also volume is V. Volumes are same. Then what about pressure? Here pressure is P1 and here also pressure is P1. Pressures are also same. And point is that temperatures also they are same. Pressure is same. Volume is same. Temperature is also same. Everything is same. So now what we are connecting? We are connecting both of them by a tube, by a bulb. Okay, ma? Now can you say after connection, air will it enter into another container or air doesn't enter? Huh? Air will never enter. Why? Pressures are same, no? Then why air will enter? Pressure will never, air will never enter into another container. Even if you connect them by a tube also, gas molecules, they will be in random motion only, they will not move from one place to another place. That is, they will not move from one container to another container even after connection. Okay, now see. Now what I am doing is, if temperature now means what, after connection. Now we are maintaining at T2, another one at T1. So let us consider, for example, T2 is greater than T1. It means what I am doing to this second container, I am heating this second container. So the temperature changes. So initial temperatures were at T1 only, no? And final temperature of container B is T2. We are changing the temperature of this one. But temperature of first container is maintained at T1 only. Temperature of second one we are changing. It means, consider you are placing this container in refrigerator, you are changing the temperature. Or you can heat this container also, no? Then also temperature can be changed. Now if I study about only this container, volume is a constant, no? But if you raise the temperature, then pressure should increase, no? In container B, let us call it as A container, this is B. Okay, ma? So I am discussing about container B. Okay. What we are doing, temperature is rising, no? Volume constant. Therefore, pressure also should rise, no? Because if volume and number of moles, if they are constant, then pressure is directly proportional to temperature, which is also called as Gay-Lussac's law. Okay, ma? So if pressure increases, what happens? Gas will enter from second container to first container. That is what will happen. Understood, no, ma? If you raise its temperature, gas will enter from second container to first container because pressure has risen, no? And this transfer of gases will continue up to which time? Until again pressures in both containers remain same. But pressures have changed, no? Initially in both of them, pressure was P1 and P1. Now finally, pressure in both of them will be P2 and P2. Are you able to understand? Initial pressures are P1, P1. Final pressure will be P2, P2. Volumes are there, they are remaining same, but temperatures are different. Temperature here it is T2 and temperature here it is T1. Chemical reaction, is it happening, ma? Chemical reaction is not happening, no? So number of moles of gas remains to be same. So again, based on the same logic, we will do this calculation. Okay. So therefore, what we say, number of initial moles is equals to number of final moles. This is after connection and this is after heating. Okay. So write down. So number of initial moles in total system I will take, ma. So N value is already equal to PV divided by RT, no? Okay, ma. So therefore N value we will calculate before heating and after heating. Pipe is already connected. So this total I can take it as one system, no? This total I can take it as one system. So what I will do, what are the initial number of moles in the first container, ma? So initial pressure is P1, initial volume is V, R is same, temperature is T1. That's all. So these are the number of moles in first container. What are the number of moles in second container? Pressure is P1, volume is V, R is R only, temperature is T1 only. In both of them, same pressure, same temperature, same volume, everything is same, no? But this total is the number of moles before heating. Before heating. After heating, now what are the number of moles in first one? Final pressure is P2, no? Final volume is remaining same, R is same, but temperature is remaining same. You are heating this one only, no? This one is not heated. Temperature of this one is T1 only, but temperature of this one is T2. So number of moles in second container. Pressure is P2, volume is V only, R is same, temperature is T2. That's all. That's all. That is my equation. No, there is only single gas, no, ma. Two gases are not there, no, for reaction. There is only one gas, that's it. So there is no concept of chemical reaction. So number of moles remains to be same. Understood? Where? Here, huh? Initial pressure P1 only, no? Final pressure will definitely change, no? Because some of the gas is entering into first container, no? If number of molecules increases, what happens to pressure? Pressure also increases, Avogadro's law. Are you able to understand? So some of the pressure is leaving this container, some of the molecules they are leaving this container, they are entering into this container. So here pressure will definitely increase. But same pressure should be present here also, no? So here also pressure will be P2. Understood? Now just do the calculation. So volume is constant, R is constant, volume is constant, R is constant, volume is constant, R is constant, volume is constant, R is constant. Clear now? So therefore P1 by T1 plus P1 by T1 is equals to P2 by T1 plus P2 by T2. That's all. No? So therefore I can also write it as 2 P1 by T1 is equal to P2 if I take common, then it is 1 by T1 plus 1 by T2. That's all. No? What I want T2 only, no, final pressure I want. So therefore 2P1 divided by T1 is equal to P2 if I take common, then it is T1 plus T2 divided by T1 T2. Okay. Therefore if I do the calculation further, okay ma, so oka flow lo unnappudu disturb cheyakudu nanu. Right? Did I do any mistake? These two na. These two you cannot add. P1 by T1, P1 by T1, 2P1 by T1. Yeah, right type now last. Okay ma. So therefore, so 2P1 by T1 is equals to P2, or I can do one thing na. So P2 is equals to 2P1 into T1 T2 divided by T1 multiplied by T1 plus T2. Okay. So T1 T1 get cancelled. So therefore what is the final pressure ma? 2P1 T2 divided by T1 plus T2. So this is the final pressure. That's my answer. Clear no? Very, very easy calculations ma. Just you should understand, read the problem very, very carefully. Draw a diagram. Goody answer lo cheppakudadu. Diagram వేస్తే మీకు క్లారిటీ వస్తుంది ఏం జరుగుతుంది ఇక్కడ. Then according to that you can proceed the problem. Okay. Okay, Sima. So a student forgot to add the reaction mixture to the round bottomed flask. It means he is taking one flask ma. A round bottomed flask means, so this is a round bottomed flask. Okay. So some gas is present, or you can say some air is present initially inside this one. So instead of placing the chemical mixture which he want to test that one, without placing anything he started heating that. Okay. So therefore what is happening in the second condition? So he didn't place anything, but he started heating this mixture. Okay. She realized, and what was the initial temperature of this one? 27 degrees Celsius, or you can write 300 Kelvin. Because 27 plus 273, 300 only, no? 300. And volumes are same now, so you can write initial volume V. Here also initial volume is V only. Okay. So after a lapse of time, she realized the mistake, and using a pyrometer, she found the temperature of flask was 477. So what is the final temperature? T1 was 300, but T2 will be 477 plus 273. How much ma? 750. 750 Kelvin. This is the final temperature of the mixture. Then the question is, what fraction of air would be expelled out? See, if you start heating this, listen very carefully. If you start heating this gas, volume is a constant, no? So if volume is a constant, pressure is directly proportional to temperature, no? So pressure automatically increases. If pressure increases, gas tries to move in upwards direction. Gas will try to move in every possible direction. So until same pressures are obtained in atmosphere also, inside this container also. See, here initially what should have been the pressure? Atmospheric pressure, no, inside this container. Why? Because outside also atmospheric pressure will be present. So what is the pressure in the atmosphere? Same pressure will be present inside the container also, because it is an open container. Container is open, no? What is the pressure of atmosphere? Same pressure will be existing inside the container also. Now when I start heating this one, now as pressure increases, this some of the gas molecules, they will move into atmosphere, no? And movement will stop after how much time? Until again pressures they will become equal, that's all. So again here the pressure is atmospheric pressure only, that is for here also pressure should be atmospheric pressure only. So until that the gas will continuously, it will move into the atmosphere. Okay ma? But whatever it may be, so consider here this much of gas has entered into the atmosphere. So here if number of moles are N1, and here if this total system, if I take number of moles to be N2, then definitely I can say N1 and N2 both are same, no? N1 is I am not discussing the gas only present inside the container. Here some of the gas has gone outside the container also. So that gas also I am taking as a system. Okay ma? The gas which has left the container, that also I am taking to be the system only. So it means this total I am taking to be one system. The number of moles, they will remain same. Are you able to understand? So previously 100 molecules were there. Now inside the container only 80 molecules are there. Then what about remaining 20? They have gone into atmosphere. But 20 plus 80, 100 only, no? So number of moles doesn't change. Are you able to understand? So therefore, based on that concept, what I am supposed to calculate, what fraction of air would be expelled. So therefore, I will do some assumptions. Let amount of expelled air, let amount of expelled air, let it be delta M. Okay, ma? This much amount of air has gone into the atmosphere. or you can say this many moles of gas has gone into the atmosphere. Okay, but he is not asking number of moles, no, he is asking what? Fraction. Fraction means how can I calculate? Fraction means number of moles gone into the atmosphere divided by initial number of moles. This is how I take a fraction. No? So these many moles have entered into atmosphere and original number of moles are Ni. So change divided by Ni will give fraction. Fraction multiplied by 100 will give percentage. Percentage he is not asking. He is asking only fraction only. So delta N divided by Ni. This is what I am supposed to calculate. Understood, Dhamma? So whatever you want to do, so you have to calculate this relation. Then that is my answer. Okay? Let us see how I can do this one. So can I write total initial number of moles is equals to final number of moles present inside this container plus delta N. Can I write like this? What is Ni? Number of moles present in the container. What is NF? Final number of moles present inside the container. And what is delta N? The number of moles which have left the container. I can definitely write like this. No? Why I am writing like this? Because every side I want to divide by Ni so that I can get the ratio delta N by Ni. Now delta N by Ni. Okay, ma? So dividing everything by Ni. What I will get? Ni divided by Ni is equals to NF divided by Ni plus delta N divided by Ni. I can write like this. So I got this required equation. No? Okay, ma? So whatever it may be, you have to get the required equation. That is our purpose. No? Now see. So therefore, Ni by Ni, 1. So 1 is equals to NF divided by Ni plus delta N divided by Ni, initial number of moles. So I want this relation only, so do one thing. So delta N divided by Ni is equals to 1 minus NF divided by Ni. I can write like this. Okay, ma? Now what is final? NF means what? Final number of moles present inside the container. This is NF, no? Okay, ma? And we know how to calculate number of moles, no? PV by RT. That's all, no? So do the calculation. So therefore, delta N divided by Ni is equals to 1 minus final number of moles. How can I calculate? P. What is the final pressure? Final pressure is P only, no? Final pressure is atmospheric pressure only. Are able to understand? No? Pressure never changes because it is an open container. No? What kind of container is this? Open container. In open container, you can never change the pressure. Always it will be atmospheric pressure only. Okay. So you can write atmospheric pressure. So PV and what is the volume? Volume is same volume, no? PV divided by R. Now what is the final temperature, ma? Final temperature is 750. That's all, no? Divided by Ni. What is Ni? Initial number of moles. Again PV is equal to nRT only, no? So N is equal to PV by RT. PV is atmospheric pressure only. Volume is same volume. R is same. And what is the initial temperature? 300. Clear, no? That's all. Now just do this calculation. Very simple. This is what I want. Okay, ma? To get this relation, this is the format of equation which I have written. This is purely our common sense only. Nobody can help here. Understood, no, ma? Purely based on our common sense, how we have to do different techniques of solving the problem. Clear? Now substitute. Now what are the terms which will get cancelled, ma? Pressure, volume, R and R will get cancelled. So therefore, delta N by Ni is equals to 1 minus 300 divided by 750. Okay. So I will do the calculation here. So delta N by Ni is equals to 750 minus 300 divided by 750. 750 minus 300 how much, ma? 450. 450 only, no? 450 by 750. So by 9, can I 5? 9 5s are 45. 9 10 15. So therefore it is 3 by 5. That is my answer. Okay, ma? So how much a fraction of air has gone outside, ma? 3 by 5th of the initial volume has, initial number of moles have gone outside, and only 2 by 5th is present inside that, what you call round bottomed flask. 3 by 5th of the gas has moved outside. Only 2 by 5 is present inside. Understood, no? That's all. Okay, ma? A statement of graphs of different laws which we have studied. How many laws we have studied? We have studied Boyle's law, Charles' law, then Gay-Lussac's law, then we have studied Avogadro's law. All this we have studied, no, ma? So I will explain 2 or 3 graphs, ma, then remaining I hope you can do them. Okay? Everything will be followed on the same process. Now see, you need not by heart any of these graphs, ma. Logic and equation is what you are supposed to remember. Understood? Now see. So what is Boyle's law? Pressure is inversely proportional to volume, no? Same equation I can write from here also. No? Actually, this equation is derived from here only. No? So pressure is inversely proportional to volume in which condition? When number of moles of a gas when they are constant. Clear, no? And temperature also should be constant. Mass of the gas also should be constant. If number of moles are constant, mass is always a constant. Clear, no? Then in this condition, pressure is inversely proportional to volume. So if I take this volume to this side, then if I write the proportionality symbol, then that proportionality symbol is K, no? And K is nothing but nRT. Okay, ma? So this proportionality symbol is nothing but nRT. This is how I can write, no? Understood, no, ma? Okay. Now, if I want to draw a graph between pressure and volume, can you say how the graph will be? If I want to draw the graph between pressure and volume, ela untundi graph? Inversely proportional, no? Pressure is inversely proportional to volume. It means that graph should be somewhat like this. This should be the shape of the graph. Because, for example, if you take any two conditions, take these two conditions, okay, ma? So P1, V1. Take one more condition, okay? So this is P2 and this is V2. Clear, no? When pressure is very large, volume is very small. Pressure is very small, volume is very large. So they are inversely proportional to each other. If one value increases, other value automatically decreases. So that is the relation between pressure and volume. Clear, no? Now, if I draw pressure volume graph for the same system in different temperatures, for example, this is one graph, this is one graph, this is one graph, this is pressure and this is volume. So let temperature is T1, temperature is T2 and temperature is T3. Then out of them, which temperature is maximum and which temperature is minimum? Okay, ma, I have taken same system. System means what? Any cylinder containing gas is called a system. Okay, ma? I have taken same type of system and I have drawn PV graph for 3 different temperatures. First of all, I have taken at normal temperature, then I have heated the gas slightly, then I have drawn second graph, then I have still heated the gas, then I have drawn the third graph. Are you able to understand? So out of them, which temperature is maximum and which temperature is minimum? T3 is maximum, you are saying. It means you are saying that T3 is greater than, T2 is greater than T1. This is what you are saying, no? Huh? How can you say?
Volume constant.
Oh, okay. If I take at constant volume, what will happen? Pressure is directly proportional to temperature. How can you say pressure is directly proportional to temperature? So if you look at this equation, are you able to understand, ma? So here nRT is a constant, no, ma? nRT is a constant. So if temperature increases, this K value also should increase, no? K is equal to nRT, no, ma, by observing this equation. So if temperature should increase, K value also should increase. If K value increases, then the product of P into V also should increase, no? Where is that product? I did not write a product of P into V also should increase. P into V is a constant. This is called Boyle's law, no, ma? Clear? If temperature increases, K value increases. If K value increases, product of P into V also should increase. So if you take at any volume, for example, you are taking this constant volume. This is only one volume, no? Then if I raise the temperature, pressure should increase, no? Then only the product of total P into V will increase. Are you able to understand, ma? Volume I am keeping constant. It means I am checking at same volume. And I have 3 graphs. So pressure is increasing. If pressure increases, product of P into V also increases. If product of P into V increases, K increases. If K increases, T also increases. అర్థమవుతుందా ఏం జరుగుతుంది ఇక్కడ? ఫేసులు చూస్తుంటే ఏందో డిఫరెంట్గా ఉన్నాయి. Is it clear, ma, what is happening? So PV is a constant, no, ma, and K value is how much? nRT. Okay. So therefore, at the same volume, I am checking for different pressures. Then I see that in different graphs, pressure is continuously increasing. If pressure increases, what happens to the product of P into V? Increases. It means K is increasing. If K is increasing, it means T is also increasing. So definitely, this is the highest temperature, next followed by T2, next followed by T1. This is how we have to analyze the graphs. Are you able to understand? Okay. Similarly, if I draw one more graph, try to say the answer of this one. Clear, ma? So which graph shall I take? I will take PV graph versus volume, and I will take PV graph versus pressure. Now can you say what will be the shape of these graphs? Product of PV versus volume. Product of PV versus pressure. Parallel to x-axis. How can you say? PV is a constant, no? ఇక్కడ ఏం రాసుకున్నాం మనం? PV is a constant. So, if volume increases, pressure will decrease. But whatever it may be, product of PV will not change, no? అదే కదా చదివింది మనం. So, therefore, graph will be a straight line. So, whatever may be the increase in volume, product of pressure into volume is not going to change because product of pressure into volume is a constant. Are you able to understand? Now, what about this graph? This graph is also parallel to x-axis. Clear, Nama? Because product of pressure into volume is never going to change. It is always a constant. Okay. One more graph. Clear, Nama? For example, if I take pressure on x-axis, 1 by V on y-axis. Now can you say what will be the shape of the graph? Straight line. Straight line to what? Origin is straight line ante evariki parallel? Parallel to x-axis or y-axis? Or in the middle? In the middle you have to draw. Okay. So this is the graph. Okay, ma? How can you say this is the graph? ఒరే మోటార్ వేసి ఆఫ్ చేసి మర్చిపోయారు మీరు అంతే ఇంకా వాటర్ నిండిపోయినాయంట ఆల్రెడీ. అక్క 4కు నువ్వు వేసింది నీ తలకాయ. సరే చూడండి మా. సో నౌ కెన్ యూ సే వై దిస్ గ్రాఫ్ ఈస్ ఎ స్ట్రైట్ లైన్ మా? See this equation here. Pressure is inversely proportional to volume, but directly proportional to 1 by V, no? Okay, ma? So, if you write relation like this, same relation, how can you say? Pressure inversely proportional to volume, but pressure directly proportional to 1 by V. Directly proportional to 1 by V. Clear, no, ma? So, therefore, pressure and 1 by V, they are directly proportional. So, this is the graph. Are you able to understand? I will draw one more graph. Clear, ma? See here, so this is pressure, this is 1 by V. Clear, Nama? I am drawing 3 graphs at 3 different temperatures. This is T1, this is T2 and this is T3. Now can you say what is the relation between T1, T2 and T3? T3 is, okay, so T3 is greater than T2 is greater than T1. How can you say? How can you say? తా చెప్పడం కదా, రీజన్ కూడా చెప్పాలి, చెప్పండి. So, if you take any one to be constant, for example, if I take 1 by V to be constant, then this is the pressure at T1, this is the pressure at T2, this is the pressure at T3. Clear, Nama? So, therefore, now you go to the relation. So, P is equals to nRT by V. Clear, Nama? 1 by V I am making constant. So, if temperature increases, what happens to pressure? Pressure also should increase. They are directly proportional, no? If 1 by V is taken a constant. Clear, Nama? So, if temperature should increase, definitely pressure also should increase if 1 by V is a constant. Clear? 1 by V is a constant, temperature is rising, so therefore pressure is also rising. It means definitely I can say T3 is greater than T2 is greater than T1. Are you able to understand, ma? Just if you remember this equation, ideal gas equation, any type of graph you can draw. No need of by hearting any of these graphs. Understood, no, ma? So, depending upon the situation, you have to select any type of graph. That's it. Okay? So, same graphs I will compare with the graph of a straight line. Now, where we have drawn, here we have drawn, no? Pressure and 1 by V, they are directly proportional. Pressure and 1 by V, they are directly proportional. So, therefore, if I write the relation, P is equals to nRT divided by V, same equation I can write like this, Nama. P is equals to 1 by V multiplied by nRT. I can write like this, no? So, same equation if you compare with y is equal to mx plus c, then what do you understand? If I compare with the equation of a straight line, what is the equation of a straight line? Y is equal to mx plus c only, no? If I compare with the equation of a straight line, Sima. So, on y-axis we are taking pressure, satisfied? On y-axis we are taking pressure. On x-axis I am taking 1 by V. Okay. So, therefore, what is the slope of this graph? Slope of this graph is nRT. This is the slope of the graph. This is y, this is x, this is m. Understood, no? Y is equal to m into x. X-axis పైన తీసుకుంటున్నాం మనం. On x-axis we are taking 1 by V. Therefore, which is the slope? nRT will become the slope. Are you able to understand, ma? So therefore, in P versus 1 by V graph, if you take theta and if you take tan theta is nothing but slope of the graph. And slope is how much? Slope is nothing but nRT. Okay. So by looking at this graph also, I can say, no, if temperature increases, slope also increases. Okay. So therefore here slope is continuously increasing. No, first graph slope is less, second graph slope is greater, third graph slope is bigger. Slope is increasing means temperature is also increasing. So like this you can compare with equation of a straight line. Clear? That's it. So see the second law, which is called as Chal's law. Clear? So what is Chal's law? We know, no, volume is directly proportional to temperature, and which one is a constant? Number of moles is a constant, pressure is a constant, mass of the gas is also a constant. These are the constants. When these values are constants, then if temperature increases, volume of the gas also increases. Clear, Nama? So from ideal gas equation, let us try to understand this one. PV is equal to nRT, so V is equal to nRT divided by P. So nR by P multiplied by T. So V is equal to K into T. What is K here? If I remove this proportionality symbol, I have to write a constant number. So this is K here. So if you compare this one, what is K value? K is a constant which is equals to nR divided by P. Understood, no? So in the previous condition, what was the constant? nRT was a constant in Boyle's law. In Charles' law, what is the constant? nR by P is a constant. Understood, no? Now you take the equation V is equals to K into T, okay, ma, and comparing with Y is equal to mx plus C. Are you able to understand, ma? So therefore, how can I draw the graph? Let us see. So this is volume and this is temperature. Okay, ma? So on y-axis we are taking volume. On x-axis we are taking temperature. So therefore, what is K here? K is nothing but slope, m. Okay, ma? And what is the value of slope? So value of slope is nR divided by P. Clear, Nama? And what is C? Y coordinate is 0. There is no Y coordinate. Y coordinate is not there means what? Graph is passing from the origin. That is the meaning of this one. No? If there is no Y coordinate, it means graph is passing from the origin. Okay. So this is the graph which I have. So volume and temperature, they are directly proportional to each other. Okay. Now if I draw the same graph for three different pressures. So this is volume, this is temperature, first graph, second graph, third graph. P1, P2, P3. Now what is the relation between P1, P2 and P3? Relation between P1, P2 and P3 is how much? P1 is greater than P2 is greater than P3. How can you see? Yes. Sima, for example, if you take at a particular temperature, okay, there are three different volumes, no? Are you able to understand? At a particular temperature, volumes are different. Now you go for the graph. See here. So V nR by P multiplied by T at same temperature. Okay, ma? If pressure increases, volume should decrease, no? See how V and P, they are related directly or inversely? Inversely proportional. It means if pressure increases, volume should decrease. If pressure decreases, volume should increase. Volume is increasing, no? It means pressure is decreasing. Okay, ma? Therefore, which one is having highest pressure? P1 is having highest pressure. Okay. So therefore, how can I draw the graph? P1 is greater than P2 is greater than P3. This is how I can draw the graph. Are you able to understand, ma? That's all very simple. Okay. So these are the laws related to Charles' law. Okay. Similarly, some more graphs. How can I draw? Let us take V by T graph. Okay, ma? So V by T versus V, and another graph is V by T versus T. Can you see? Straight line. Why? Because V is equal to K into T, no, ma? So therefore, what is V by T? V by T is a constant. Clear, no? V by T is a constant. So whatever may be the volume, whatever may be the temperature, ratio of V by T always remains constant. So therefore, graph will be a straight line parallel to x-axis. Understood, no? So this is how you have to analyze the graphs. And if you draw this graph, now you take theta here. So tan theta is nothing but what? Slope. Already we have written, no? Tan theta is called slope. And slope is how much, ma? nR divided by P. So this is the slope of this graph. Clear, no? So like this, can't you draw graphs for, what is the third law? Gay-Lussac's law also you can draw, no? Huh? Try to draw. I need not explain, Mama. I hope you can draw them. So write the equation of Gay-Lussac's law and draw what are the different, what you call graphs which are possible. Okay, come on. Draw cheyandi. Okay, ma. Now these are the equations of Gay-Lussac's law, ma. So previously we have drawn graphs for Charles' law, no? Volume is directly proportional to temperature. Here pressure is directly proportional to temperature. So in the same condition, just wherever you see V, there you write P. Wherever you find P, there you write V. That's all. So you will get the total equation. Clear, Nama? So again see here. So pressure is directly proportional to temperature, Nama. So P is equal to K into T. Okay. So P by T should be a constant. So therefore pressure and temperature, they are directly proportional, no? Now we are drawing for 3 different volumes. V1, V2 and V3. Okay. So definitely I can say V1 is greater than V2 is greater than V3 because at same temperature, if I take same temperature, pressures are increasing, no? So pressure can increase in which condition? Pressure can increase only when volume reduces. So therefore here volume should be maximum, next lesser volume, next further lesser volume. And this already we have studied, no? P by T is a constant, no? P by T is a constant, so variation of P by T with respect to P is a straight line. It means P by T doesn't change. See, similarly P by T with respect to temperature also does not change. That is the graph which is called as graphs for Gay-Lussac's law. Okay? Okay, Sima. So these are 4 graphs which are given, ma. Out of these 4 graphs, we have to identify how many of the graphs they represent Boyle's law and how many of them disagree with Boyle's law. Clear? What is Boyle's law? Basically, pressure is inversely proportional to volume. This is Boyle's law, no? Or I can write the product of P into V is a constant. Okay, and what is that constant? PV is equal to nRT. This is called as constant K. Okay. Now let us see how many of graphs they are following. So pressure is inversely proportional to volume. This is satisfied, no? Pressure is inversely proportional to volume. It cannot be a straight line. So this graph cannot be followed. Clear, Nama? And pressure into volume, it is a constant. Whatever may be the change in pressure, whatever may be the change in volume. So this graph is also satisfied. Okay. So first graph, fourth graph, they are satisfied. Third one is not satisfied. Now let us go for this second graph. So here values are given in terms of logarithms, Nama. So we will also apply logarithms here. So PV is equals to, so if I look at this graph, so PV is equal to nRT, it is a constant. Okay. So if I apply logarithms, so log P plus log V is equal to log K. Okay. Same relation I can write it as log P is equals to minus log V plus log K. Now we have to compare this one with y is equal to mx plus c. Okay. So therefore log P we are taking on y axis. Clear, Nama? Log V we are taking on x axis. So therefore m is equal to minus 1. So slope of this graph is minus 1. Okay. And what is the y-intercept? Y-intercept is equals to log K. Okay. So this should be the possible graph. It means this graph of log P and log V, it should be a straight line. Okay. But here a straight line is not given. So therefore this graph is not correct. So therefore first graph and fourth graph they are correct. Second one and third one they are wrong. Okay. Concept which we are studying is we want to find out the molecular weight of a gas, or we can calculate molecular weight of a mixture of gases from ideal gas equation. So what is meant by ideal gas equation? PV is equal to nRT. This is called ideal gas equation, Nama. So I can write down PV is equals to N can be written as total mass divided by molecular weight, no? Or molar mass multiplied by R into T. Can I write like this? We know how to calculate number of moles, Nama. Total given mass divided by molecular mass. Okay. So total volume divided by volume of 1 mole of gas at STP. Clear, no? Or you can calculate total number of molecules divided by Avogadro number of molecules. So these are the different methods of calculating number of moles. So therefore N I am writing in terms of total mass of the gas divided by molecular mass. Clear, no? So therefore M can be written as small m divided by PV multiplied by R into T. I can write like this also, no? So therefore if you take the ratio of mass and volume, then it is called density, no? Density is called mass by volume, no? So therefore what I can write? molecular mass is equals to density of the gas divided by pressure of the gas multiplied by R into T. So I can write like this also. Clear, no? So this is the equation to calculate molecular weight of a gas or molar mass of a gas or molecular mass of a gas. Clear, no? So density divided by pressure multiplied by R into T. This is one equation. Understood? Now we will write some cases, ma. Case number 1 is if there is single gas present in the container. So what is meant by single gas present? There is only one gas present in the total container. Then what is M? M is molecular mass of the gas. Clear, no? So for single gas only. Okay. Then what is meant by density? Density of the same gas. Density of single gas. Clear, no? Similarly, if I take pressure, then this is the pressure of single gas. That's all, no? So instead of taking single gas, if I take a mixture of gases, what is meant by mixture of gases, ma? So some 2 gases, 3 gases, 4 gases are present in the same container. Are you able to understand? So more than one gas also can be present, no, ma? So in that condition, what will be M here? M will be the molecular weight for mixture of gases. Okay? So molecular weight for what? For mixture of gases. Clear, no? Similarly, now what is meant by D here? D means what? Density of total mixture of gases. Okay? Similarly, what is meant by P? P is the total pressure of all the gases. Total pressure of all gases. Are you able to understand? Same equations we can write in different methods. That's it. Okay. So M is equals to D by P multiplied by RT. This you can use for single gas also or for a mixture of gases also. If you are taking a mixture, for total mixture there will be some molecular weight, no? That is molecular weight of the mixture. D is the density of total mixture of gases. Clear, no? And P is the pressure exerted by all the gases. Each gas will give individual pressures, ma. Okay, so total pressure is the sum of all pressures, which is called as Dalton's law of partial pressures. Okay, now see, ma, we will write one very important case here for mixture of gases. For mixture of gases, so consider there are 3 gases, ma. So consider this is gas A, next one is gas B, and the third one is gas C, and total values here we will write down. Okay, gas A, gas B, gas C, and total value. Clear, no, ma? So all of them, they are present in a single container, ma. Gas A, for example, hydrogen gas, helium gas, oxygen gas, all of them, they are present in the same container. Okay, then can you say gas A will occupy how much volume? Total volume of the container is V. Total volume of the container is V. Then first gas will occupy how much volume? Can you say? It will occupy total volume. That's all, no? Already we studied, no? What is the property of gas? ఆశిష్ విద్యార్థి మనలోకంలోనే ఉన్నావు కదా, మనలోకంలో ఉన్నావు కదా, పెళ్లి గురించి ఆలోచిస్తున్నాము అని లేదు కదా. ఓకే, ఓకేమ్మా. చిన్నప్పుడు మా అమ్మ అడిగేది అనమాట, ఒరే పెళ్ళి ఎప్పుడు చేసుకుంటాడు, 13 ఏళ్ళు వస్తానే చేసేమా నాకు పెళ్ళి అనేవాడిని నేను. అట్లా ఆశిష్ కూడా తొందరపడతాడేమో అని. ఓకేమ్మా. సో గ్యాస్ ఏ, it will occupy total volume of the container. Whatever may be the possible volume, gas will occupy all the possible volume. Clear? So if volume of the container is A, then gas A will occupy all the volume. Similarly, gas B also will occupy all the volume. Gas C also will occupy all the volume. Total volume is also V only. Clear, no? And temperature of first gas, if it is T, then what is the temperature of second gas? T only. Temperature of third gas, T only. Temperature of total mixture also T only. That's all, no? If you mix 2 gases, if initial temperatures are different, but after mixing final temperature will be same. So temperatures also will remain same. Number of moles of first gas, I can call it as Na. Number of moles of second gas, that may be different, Nb. Number of moles means number of particles of gas. Clear, no? And what about gas C? It also may be different. Now what is the total number of moles? Na plus Nb plus Nc. That's all, Nama. 10 molecules of oxygen, 10 molecules of hydrogen, 10 molecules of helium, they are present. So total how many molecules? 30 molecules are present. Clear, Nama? So therefore I can say, so Na plus Nb plus Nc. This is the total number of moles present in that container. Understood, Nama? Similarly, if I want to write about pressure exerted by first gas is Pa. Okay? Pressure exerted by second gas is Pb. Pressure exerted by third gas is Pc. Then what is the total sum of pressures exerted in the container by all the gases? So Pa plus Pb plus Pc. So Pa plus Pb plus Pc. So this point you should always remember. Are you able to understand? So students make mistakes in understanding this concept also. So if N1 moles of gas is present, it is not that it occupies only some volume of the container. It occupies total volume of the container. Understood, Nama? So volume is occupied equally by all the gases. Temperatures will be same after mixing. Before mixing, it is a different condition. But after mixing, every gas will have same temperature. Number of moles may be different. And therefore, pressures also may be different. Are you able to understand, Ma? So this is one point. Okay? Understood, Nama? So therefore, what is the formula I can write for mixture of gases? Okay? For mixture of gases, I can write down. To calculate molecular weight of a mixture, I will write M mixture is equals to D by P multiplied by R into T. Okay, ma? So D means the density of the mixture, pressure means total pressure. So I can write like this. Understood, no? Okay, ma? Similarly, we have one more formula to calculate a mixture of gases, ma. What is that? Let us see. Total mixture of the density. That either he may give or he may ask us to calculate also, depending on the question. This is the formula. Clear, no? So another equation to calculate density of a mixture. Okay, ma? So there is one more formula whose derivation I am not writing, just formula I am writing. So molecular mass of total mixture of gases, I can write it is M1 x1 plus M2 x2 plus dash 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 divided by x1 plus x2 plus dash dash dash. So any number of gases may be present. 2 gases, 3 gases, 4 gases, anything can be present. Are you able to understand? Now what is meant by M1, M2 here, ma? M1 and M2 means what? M1 is the mass of molecular mass of first gas. M2 is the molecular mass of second gas, like this. Understood, no? So then what is X here? X can be number of moles also. Okay, ma? Mole fraction also. Mass percentage also. Or just you can call mass also. Are you able to understand, ma? So in the place of X you can write anything. If value is given in number of moles, you can substitute number of moles. X1 is the number of moles of first gas, X2 is the number of moles of second gas, like this you can write. Or instead of number of moles, if mole fraction is given, then you can write mole fraction also. Similarly, instead of mole fraction, if mass percentage is given, then also you can substitute. Similarly, instead of just mass of the gas is given, then also you can substitute. Are you able to understand? So this is one more equation to calculate molecular mass of mixture of gases. Understood, Amma? Molecular mass of 1 mole of a gas. Mass ki total mass ki molecular mass ki confuse avadandi. Okay? So what is called M1 here? M1, M2, what are they, ma? They are molar masses. Or you can call them as molecular masses, or you can call them as molecular weight, or you can call them as mass of 1 mole of a gas. Okay? So there are many methods in which we indicate mass of 1 mole of a gas. Understood, no? Come on. Make a note up to here. Okay, ma? So next concept which we are studying is Dalton's law of partial pressures. See, ma, here consider this is a container in which 3 gases are present. 3, 4, any number of gases can be, more than one gas is present. Clear, Nama? Then what happens is, total pressure which is experienced by this container. Okay, ma? Actually, why container will experience pressure, ma? See, ma, here, inside this container, there will be gas molecules or gas atoms, no? Molecules will be present. And at normal temperature or any temperature except at minus 273. Except at minus 273 at any temperature. Even at minus 272 also, these molecules, they will be moving. Or if it is a solid, the molecules of a solid will be in vibration. Okay, ma? So these gas molecules, they will be moving in random directions, no? So in the process of moving, they go and strike with the surface of the container. Okay, ma? So molecules continuously, they will be undergoing collisions with the surface of the container. Collision means it is giving some force, no? Force per unit area is called pressure. So on the container, who will give pressure actually? These molecules only, they are giving pressure because of continuous collisions. Surface of container, though, eppudu avi collide avutune untayi avi. And force applied per unit area is nothing but pressure. Okay, ma? So therefore, total pressure exerted by all the gases will be how much? That is the sum of pressure exerted by first gas plus pressure exerted by second gas plus pressure exerted by third gas. This is understandable only, no? The rocket science emundi ikkada. Total pressure is nothing but pressure exerted by first gas plus second gas plus third gas. That's it. Understood, ma? And what is this PT? PT is nothing but total pressure. Okay? And what is this PA, PB, PC? They are called as partial pressures. Partial pressures. Partial pressures means what, ma? Pressure exerted by each gas is called partial pressure. Are you able to understand? So total pressure is equals to the sum of individual pressures. That is called as Dalton's law of partial pressures. Very simple concept, you know. So write down the statement of this one. So the total pressure exerted by gas is the sum of, or you can say is the algebraic sum of, algebraic why we are writing, because pressure is a scalar quantity, no, it doesn't have any direction. So vector sum we are not taking, we are taking algebraic sum. Okay, algebraic sum of partial pressures exerted by individual gases. Okay, ma? This is called as Dalton's law of partial pressures. Okay. So listen, ma. See, ma, here one point I can understand is that if first, listen very carefully, if first gas is having 10 molecules, second gas is molecules I am writing. Second gas is having 30 molecules in the same container. Okay. And third gas is containing of 100 molecules of gas number 3. Then which gas will exert more pressure on the container, ma? Definitely this gas will exert more pressure, no? Why? More number of molecules are there. More number of molecules, they continuously they will be striking with the walls of the container, no? Are you able to understand, ma? And this gas will exert lesser pressure when compared to third gas. This will exert still lesser pressure. So therefore, can I say that pressure is directly proportional to number of molecules of a gas? Definitely I can say, no, ma? Okay. So this is the most simplified model of understanding partial pressures, ma? Clear? So pressure is directly proportional to number of molecules. If number of molecules increases, pressure also increases. So, and number of molecules depends on moles of gas only, no? First gas is 10 moles, second gas is 30 moles, third gas is 100 moles. Definitely third gas will exert more number of pressure. So therefore what I can write, again I can write pressure is directly proportional to number of moles of a gas also. Okay. Therefore I can write, if I want to compare these two gases or three gases, I can write P1 by P2 or PA divided by PB. Pressure exerted by first gas divided by pressure exerted by second gas. It means it is ratio of pressures, no, ma? And this must be equal to the ratio of number of moles of a gas also. Okay. This is a very, very, very important relation by which we can do many, many kinds of problems. Okay. So the ratio of pressures is always equal to the ratio of number of moles of that particular gas. Okay. So statement wise, how can I write? The ratio of pressures of a gas of two gases is exactly equal to the ratio of moles of those gases. Understood, Nama? So what is the ratio of pressures? Same will be the ratio of number of moles also. Understood, no? Okay, ma? Similarly, we can write down. So instead of like this, I can write equation in another form also. I can write. Okay, ma? I can also write pressure of a gas divided by total pressure is equals to number of moles of that gas divided by total number of moles. I can write like this also, no? Understood, Nama? Instead of comparing only two gases, I can take a fraction with total pressure also. And similarly, I can take moles in terms of total number of moles also. Here I have compared two gases, no? There what I have done, I have compared the pressure of one gas with total pressure of the gas. Similarly, I have compared number of moles of one gas with total moles of a gas. So I can write like this also. Understood, Nama? So therefore, this is one method of writing. Or same relation I can write like this also. This relation, how I can write? PA is equals to PT multiplied by NA divided by NT. I can write like this also. Okay. Now what is meant by PA? Partial pressure. PA means pressure of only one gas, no ma? That is called partial pressure. Okay. So partial pressure is equal to, now PT, total pressure. NA by NT. NA, moles of one gas. NT, total moles. Then it is called mole fraction, no? Fraction of moles is called mole fraction. Clear, Nama? So partial pressure is equals to mole fraction multiplied by total pressure. I can write like this also. So this is also a very famous relation. Okay. So partial pressure of any gas is equals to mole fraction of that gas multiplied by total pressure of the gas. Understood, Nama? So these are the different methods of understanding Dalton's law of partial pressures. Clear? Understood, Nama? Very easy. Okay, ma? Now see. So a container has 1 mole of nitrogen gas and 1 mole of hydrogen gas at 300 Kelvin. So what is the volume of the container? Volume of the container is 10 liter. Okay. Then calculate the total pressure of on the container before reaction and after reaction. Understood, Nama? So first of all, we will study before reaction. It means before these two gases they react, what will be the pressure on the container. Understood, Nama? So therefore, how can I write? See, ma, here N1 is equal to N2 is equal to 1, no? Number of moles of nitrogen, number of moles of hydrogen, they are same. So therefore, already we studied that P1 by P2 is equals to N1 by N2, no, ma? So this is 1. Therefore, P1 is equals to 1 into P2. So therefore, pressures are also same. It means that pressure exerted by which gas? Nitrogen gas on the container and pressure exerted by hydrogen gas on the container, both are same. Both gases will exert same amount of pressure. But that's not what he is asking. No, he is asking total pressure. So I can use ideal gas equation. So PV is equals to nRT. Are you able to understand, ma? So pressure I can write P1 plus P2 partial pressures, no, ma? And total volume of the gas is always same. Okay. Number of moles are how much? 1 plus 1, 2. 2 moles of gas is present. Or you can write one thing. You can write Na plus Nb multiplied by R into T. You can write the equation like this. So this is the equation for one gas. Same equation I am modifying for a mixture of gases. Is it clear? Okay, ma? Therefore, So total pressure is nothing but P1 plus P2 is equal to PT, no ma? Therefore, what I can write, total pressure multiplied by volume. What is the volume of the container? 10 liter. Clear, no ma? So this is equals to Na plus Nb. How many number of moles? 1 plus 1? 2 moles multiplied by R multiplied by what is the temperature? Temperature is how much? Where is the temperature? 300 Kelvin. So it is given in Kelvin only, no? You need not convert into another scale because Kelvin is the SI unit of measuring pressure. So therefore do the calculation, 1 0 and another 0 get cancelled. So total pressure is equals to 60 R. So 60 R is the pressure. Understood, no? That's it. So one more question is there, no? After reaction. So let us see. So after reaction, that is after hydrogen and nitrogen, they will get reaction with each other. So hydrogen plus nitrogen, they give rise to NH3, no ma? But equation, is it balanced? No. So how to balance this one? 2N2 is there, I will place a 2 here. Clear, no ma? But how much is there here? 3 is there, but here 2 is there. So what can I do? I can write like this. 3H2. Okay, ma? So 3H2 plus N2, they give rise to 2NH3. Are you able to understand? So if reaction should happen completely, satisfied to 3 2s are 6, 3 2s are 6. Okay, ma? If reaction should happen completely, it means every molecule of hydrogen and every molecule of nitrogen, if they should react with each other, then 3 moles of hydrogen should be present and 1 mole of nitrogen should be present. Understood, no? So here I will write after reaction means in this condition also I will write 2 cases, ma. How can I write 2 cases? So here only 1 mole nitrogen and 1 mole hydrogen is given, no ma? So therefore, how much part of nitrogen will react and how much part of hydrogen will react, that we have to see here. Okay? I will do one thing, I will divide everything by 3 ma. Okay? So 2NH3 will form, no? Instead of this equation, I will do one thing. I will write H2 plus N2. N2 should be how much? 1 by 3. And they gives rise to NH3. Clear, no ma? So therefore, how many moles will form here? Balance this equation. So hydrogen only 1 mole is there, no ma? But nitrogen will react. How much part of nitrogen will react? Only 1 by 3rd of nitrogen will react, no, according to this one. So here I have written 1 by 3. Now how can I balance this one? How can I balance this one? 3 by 2 can I write? Or 2 by 3 now? Now is it balanced, ma? 3 by 2 n is there. Here only, no. I have to write it as 2 by 3. Now it is satisfied, no? Now the equation is balanced. Are you able to understand, ma? So therefore, 1 mole of hydrogen will react with how many moles of nitrogen? Only 1 by 3 moles of nitrogen will get reacted with each other. Then how many moles of NH3 will form? 2 by 3 moles of NH3 will form. Are you able to understand? Then remaining how many moles of nitrogen is left with? Only 2 by 3 moles of nitrogen is left. Okay. So you calculate the pressure of 2 by 3 moles of NH3 and 2 by 3 moles of nitrogen. Then add both of them. That will be the total pressure after reaction. Have you understood anything? So that's the reaction which I have written, Nama. To form NH3, 3 moles of hydrogen and 1 mole of nitrogen should react. So therefore, but how much hydrogen is given? Only 1 mole of hydrogen is given. So 1 mole of hydrogen can react with how many moles of nitrogen? Here it is only 1 by 3rd, no? So I am writing 1 by 3. 1 mole of hydrogen can react only with 1 by 3rd of nitrogen. Are you able to understand? Then again, if you balance this one, then I have to write 2 by 3 of NH3. Understood, no? 2 by 3 of NH3 means so only this much amount moles of NH3 is formed. So hydrogen is completely utilized, no? 1 mole of hydrogen is given and 1 mole is completely utilized. How many moles of nitrogen is present? 1 by 3 is utilized. Remaining nitrogen is not reacted, no? What is the remaining nitrogen? 2 by 3rd of nitrogen is present. So therefore you have to calculate pressure because of how many gases? 2 gases. So 2 by 3 moles of NH3 and 2 by 3 moles of nitrogen. So calculate total pressure, that will be the pressure after the reaction. Are you able to understand? This is how we have to do it. Come on, try to do. Understood, Nama? So now do the calculation. So therefore, finally how many moles of gases are left with Ma? So 2 by 3 moles of NH3 is left and 1 by 3rd mole of nitrogen is utilized. What is the remaining nitrogen present? 2 by 3 moles of nitrogen is present in the gas. Is present in the cylinder. Understood, Nama? Therefore, do the calculation. Again, same concept. So, P1 plus P2 is equals to N1 plus N2 into RT. That's all, no? So, what is the pressure of first gas? 2 by 3. Pressure of second gas? 2 by 3. Total pressure I want to calculate. Now, I will make it as PT. Number of moles of first gas? 2 by 3. Number of moles of second gas also? 2 by 3. Multiplied by R into temperature is 300. Clear, Nama? So, therefore, what is the total pressure? 4 by 3 multiplied by R into 300. So, volume I forgot, no? Sorry. Volume is how much, ma? Volume is 10. So, multiplied by 10. So, therefore, PT is equal to how much, ma? So, 10 and this one get cancelled. So, 3 1s are 3 10s are. So, how much, ma? 40 R. That is my answer. Okay. So, final pressure in the container is how much? It is only 40 R. Is it clear? So, this I am multiplying with V. I forgot to multiply with V here. అర్థమైంది కదా ఎలా చేస్తాం? వెరీ సింపుల్. మళ్ళీ క్వశ్చన్ వినండి. Sima. So 4 grams of hydrogen and 32 grams of SO2 are present in a gaseous mixture at NTP, normal temperature and pressure. Normal temperature and pressure means what? 20 degrees Celsius and 1 atm pressure, 1 atmospheric pressure. Okay? And STP means what? 0 degrees Celsius, 1 atmospheric pressure. Then the question is, what is the partial pressure of hydrogen when compared to the partial pressure of sulfur dioxide? So that is when compared to the pressure of SO2, hydrogen is giving how much amount of pressure? Comparison I want to calculate. Okay? So anybody, can you say how can I do this calculation? So what he is asking actually, pressure of H2 divided by pressure of SO2. This is what he is asking. No? If I can know this ratio, then I can say what is the partial pressure when compared to hydrogen. Sorry, when compared to SO2. This is comparison with SO2 only, no? So can you say how can I do this calculation?
Number of moles of hydrogen divide
ఎవరిని డివైడ్ చేయాలి? Sima. Already we have studied a relation, Nama. The ratio of pressures is equal to ratio of number of moles. Already we have done this calculation. No? This is the relation which we are supposed to use here. Okay. Number of moles, how can I calculate? Number of moles is total mass divided by molecular mass only, no? So first of all I will calculate for hydrogen, then I will calculate for sulfur dioxide. So for hydrogen, what is the mass given? 4 grams. So 4 divided by, what is the molecular mass of hydrogen? 2. So 2 moles of hydrogen is present in the container. That's all, no? What about SO2? So 32 grams of SO2 is given. What is the molecular mass of SO2? 64. So this is also 2 moles. Both are 2 moles only, na?
0.5, 1 by 2.
Sorry. So 32 by 64 is half mole. 0.5 moles of SO2 is present in this container. Okay, now substitute here. So the number of moles of hydrogen is how many, ma? 2. Number of moles of SO2 is 1 by 2, so 4. That's all, no? Clear? Therefore, pressure of hydrogen, partial pressure of hydrogen is 4 times when compared to partial pressure of sulfur dioxide. That's all. This is the method of calculation. Understood, no? That's very easy. Okay? And this molecular masses, you should remember, ma, for at least 1 to 50 atomic numbers, you have to remember their molecular masses also. So in periodic table, you have to by heart all the elements group wise, atomic numbers at least up to 50, atomic masses at least up to 35 to 40. Then that is enough. ఆవేశం ఎక్కువ మేడంకు ముందే. Okay, ma? Now see. So question is that equal weights of ethane, C2H6, and hydrogen are mixed in an empty container at 25 degrees Celsius. Ma. Clear? Weights are equal. Weights means in the sense masses are equal. Okay, ma? If mass is equal, weight is also equal only because we are present on the same planet, no? So no problem. So the fraction of total pressure exerted by hydrogen is. So what he is asking, ma? So pressure exerted by hydrogen divided by total pressure. This is what he is asking. No? Pressure exerted by total pressure is called fractional pressure. Okay, ma? So therefore, this relation I can also write it as number of moles of hydrogen divided by total number of moles also I can write, no? Because already we have studied what is the fraction of pressure. Same will be the fraction of number of moles also. Okay, ma? Number of moles fraction ఎంత ఉంటుందో pressure fraction కూడా అంతే ఉంటుంది. Because pressure depends on number of molecules. Number of molecules is decided by number of moles of a gas. Okay. Now do the calculation. So number of moles, how can I calculate? Mass is given, no ma? So therefore weight is given. Mass divided by molecular weight. Weight divided by molecular weight is called number of moles. This is the formula, no? Small m divided by capital M, or you can write weight divided by molecular weight. Anything, both are same. In physics we use weight and mass to be synonyms, ma. Okay? Because chemistry people, they don't know difference between mass and weight, no? So they will use mass and weight to be synonyms only. Are you able to understand? So mass and weight both are same in the case of chemistry. Okay? So therefore, now do the calculation. So partial pressure of hydrogen divided by total pressure is equals to, so number of moles of hydrogen. Masses are same, no? So weight is same. W divided by, what is the molecular weight of hydrogen? Molecular of hydrogen is 2 divided by. So molecular weight of total gas I want, so number of moles of total gas I want, no ma? So weight divided by 2 plus weight divided by, and C2H6. C2H6 molecular weight. So C, 24 plus 6, 30. That's all. Clear, no? So weight will get cancelled. So therefore what I am left with, 1 by 2 divided by LCM, if I take 30, then it is 15 plus 1. Okay, ma? So 1 by 2 multiplied by 30 divided by 16. So 2 1s are 2 15s are. So it is 15 divided by 16. That is my answer. 15 is to 16. Understood, no, ma? That's it. So after Dalton's law of partial pressure, the next concept which we are studying is Graham's law of diffusion. So what is meant by Graham's law of diffusion? See, my any gas, if it is at higher concentration, Subara. Oh, okay, ma? So if any gas, if it is at a higher concentration, then always it tries to flow from higher concentration to lower concentration, so that density of the gas, or you can say concentration of the gas, or pressure of the gas reduces. So that process is called as diffusion of a gas. Okay, ma? So the process in which the density of the gas reduces, concentration reduces, or you can say pressure of the gas reduces, that concept is called as diffusion. Okay, ma? So diffusion of a gas, it depends on these many factors, ma. So R is proportional to A into P divided by root D. Or you can write separately, R is proportional to A, in which condition when P and D are constant. That's all. So I can say rate of diffusion is directly proportional to pressure, in which condition when A comma D, when they are constant. Similarly, I can write R is inversely proportional to root D, in which condition when area and pressure, when they are constant. Are you able to understand, ma? So if you combine all of them, then I will get this relation. So R is equals to A into P divided by root D. Now what is A here? A means area of the hole which you have made in that container. Okay, ma? Or you can call it as area of the orifice. Area of orifice. Okay, ma? Orifice means hole. So if you make a hole in a container, gas leaks out, no, ma? Why gas leaks out? Because inside the container pressure must have been greater. So gas always tries to flow from higher pressure region to lower pressure region. So A is area of the orifice. What is P? P is called pressure of the gas. Okay, ma? And D is called as vapor density of the gas. Okay? Or D you can write it as V into D also, vapor density of the gas. Are you able to understand, ma? So these are the three conditions on which rate of diffusion of a gas is depending upon. Rate of diffusion means how much gas is diffused per second. That is called as rate of diffusion. Okay, ma? Now here also I can write, see ma, I will take this relation. So R is proportional to 1 by root D. In which condition? When area of the orifice and pressure, when they are constant, then I have to write this relation. Are you able to understand? And here there is one more relation. Molecular weight of a gas, this is equals to 2 times of vapor density of a gas. So this is one more relation which you should remember. Okay, ma? What is the relation between molecular weight of a gas and vapor density? So molecular weight of a gas is 2 times of vapor density of a gas. Clear? So therefore, if R is directly proportional to 1 by root D, then also I can write R is directly proportional to 1 by root M also, no? I cannot like this also, no? Because molecular weight and vapor density, they are directly proportional. So here instead of vapor density, I can write capital M also. What is meant by capital M? Molecular weight of a gas. Okay, ma? So this is a very important relation, and this relation itself is called as Graham's law of diffusion. Are you able to understand, ma? So Graham's law of diffusion says that the rate of diffusion of a gas, it is inversely proportional to root of molecular weight of a gas. So all these are gas laws only, and this is a very important derivation which we have done. Ma. Are you able to understand? Okay. Similarly, we can write, see ma, if, and here this is proportional to root M in which conditions? Conditions are A, comma, P, comma, T. T means the temperature. Okay, ma? They should be constant. Are you able to understand? Area of the orifice, pressure and temperature. Pressure and temperature, they are interdependent. Okay, ma? So area, pressure and temperature, if they are constant, then I can write this relation. Okay. And if pressure is a variable, if pressure is a variable, okay, then how I have to write? Then I have to write R is proportional to, here I have pressure, no ma? So pressure divided by root M. This is how I have to write. So if pressure is a constant, then I can remove pressure. But if pressure is a variable, then I have to include pressure also, no? So R is proportional to P divided by root M. This is how I can write. Are you able to understand? Okay, ma? So after that, if I take 2 gases, now here I have discussed only about one gas, no? Now if I take a mixture of gases, or if I am comparing 2 gases, okay? So if I take 2 gases, then how I can write? I can write R1 by R2 is equals to square root of M2 divided by M1. I can write like this, no? Where R1 is the rate of diffusion of first gas, R2 is the rate of diffusion of second gas. So R is inversely proportional to root M, no ma? So if I write R1 by R2, then here I have to write M2 divided by M1, because they are inversely proportional. And here what are constants here? Here pressure is a constant, area of orifice is a constant, temperature, it is a constant. These are the variables which are constant. Are you able to understand, ma? Now if pressure is a variable, if pressure is also a variable, then can you say how can I change this equation? If pressure is also a variable, then I have to include pressure also. And what is the relation between rate of diffusion, pressure? Directly proportional, inversely proportional? Directly proportional, no? So therefore how I have to write? R1 by R2 is equals to P1 by P2 multiplied by square root of M2 divided by M1. So I can write like this also, if pressure is a variable. Okay, ma? So whenever he gives the gases in terms of moles, mole fraction, mass of the gas, if he measures these kind of things in the question, then it means definitely pressure is a variable. Are you able to understand, ma? What are the terms you have to search for in the question? Number of moles, mole fraction, weight of the gas, mass of the gas, 2 different gases. So if he is comparing about 2 different gases, and if he is using this terminology, then you have to remember definitely pressure is also a constant. Because pressure depends on what? Pressure depends on what? Pressure depends on number of molecules or number of atoms, no? So if number of atoms or number of molecules will change, pressure will change, no? Clear? For example, if you take 1 mole of hydrogen and 2 moles of oxygen, which will give more pressure on the container? 2 moles of oxygen will give more pressure, because 2 moles are there means double molecules are present, double molecules of oxygen are present when compared to molecules of hydrogen. So automatically oxygen will give more pressure. So if pressure is also a variable, definitely you have to include pressure also in the given relation. And in the question, if he gives 1 mole of hydrogen and 1 mole of hydro-oxygen, then pressure is not a variable. No? Are able to understand? Initial pressures remain to be same, because already we have studied Avogadro's law. No? What is Avogadro's law? If you are taking containers of similar sizes of the containers, if they are same, that is volume if it is same, pressure if it is same, temperature also if it is same, then every container will have same number of molecules. That is Avogadro's law. No? Are able to understand? Ma? So similarly, if volume is same, temperature is same, pressure is also same, it means definitely number of moles of the gas also should be same. So if number of moles, if they are same, then pressure is not a variable, pressure is a constant for both of them. Then you need not use pressure here. Are able to understand the difference? Ma? So you better make a note of it. Okay. So note point. So check for pressure. If it is variable or not. Okay, ma? If same number of molecules exist, same number of molecules, I can call it as moles also, no? Ma? Moles also. If number of moles are equal, the number of molecules are also there equal. So if same number of molecules exist, then pressure is a constant in both the gases. Clear, no? Ma? But if number of molecules, if they are not equal, then ఏమైందిరా ఇప్పుడే టిఫిన్ చేసినా కదా. Are able to understand? So always you should check for pressure. Okay. Similarly, we will write some cases also. What are the cases we will write? Cases are there if you want to write the rate of diffusion in terms of length of a gas. For example, he will give some questions. He will give two molecules on different sides, and there will be a glass tube. Okay, ma? So diffusion of one gas and diffusion of other gas may be different, So some gas they travel faster, some gases they travel slowly. Are you able to understand? So if they travel in a particular length of a glass vessel, so what is the distance covered by each each gas? So questions can be asked like this also. So we will do one question on that. So therefore, if question is given on in terms of length traveled by gas, it means he says that oxygen gas has traveled 8 centimeters of length, oxygen gas, helium gas has traveled another centimeter. So like that question can be given in terms of distance traveled by gas also. Clear, no? Then in that condition, the rate of diffusion R1 by R2 is equals to okay, Sima. So we have studied equations of rate of diffusion, no? Now we are studying some more equations for rate of diffusion. So first one is rate of diffusion in terms of length traveled by the gas. So previously we have done one problem, no? For example, in this one NH3 gas was present, and here HCl gas was present, and both of them they were connected by some tube. Are you able to understand, ma? Then the gases start diffusing, and each gas covers a different distance depending on their molecular masses. That's what we have studied, no? So therefore, if I know what is the length traveled by each gas, for example, if ring was formed here, ring means NH4Cl. NH4Cl ring, if it formed here, then NH3 would have traveled this much distance, and HCl would have traveled this much distance. That's all, Rama. So what is the length traveled in a particular time? Similarly, what is the length traveled by second gas in a particular time? That is equals to square root of m2 divided by m1. That is the actual meaning of this one. Clear, Nama? Similarly, in terms of rate of diffusion, in terms of number of moles of gas which has diffused. So here N1 doesn't indicate the initial number of moles. N1 indicates the number of moles of the gas which has gone out of this cylinder. Number of moles which has escaped, which has diffused. Are you able to understand? So N1 by T1 multiplied by T2 by N2, it is equals to square root of M2 divided by M1. Clear, Nama? Similarly, in terms of volume of gas diffused, so this is length traveled, this is number of moles, and this is how much volume of the gas has diffused out of the holes or out of the opening. Then again, same format of formula. V1 by T1 multiplied by T2 by V2 is equals to square root of M2 by M1. Clear, Nama? And the last one, in terms of mass of gas diffused. Are you able to understand? How much mass, or you can say how much weight of the gas diffused. Already we discussed in chemistry, mass and weight both are same, Nama? So therefore, W1 by T1 multiplied by T2 by WT is equals to here square root of M1 by M2. In all this you will write M2 by M1, but here you will write M1 by M2. So W1 and W2, they are not initial masses. They are masses which have diffused, which has gone outside the cylinder. That is called W1 and W2. Understood, no? Already you have written, no? Okay. So this is the question. Two balloons are filled with equal moles of hydrogen and helium. It means one balloon I am filling with hydrogen gas, and in the second balloon it is filled by helium gas. Okay, ma? So which balloon? So I am making same size holes. It means area of the orifice is constant. That is what is meant by same size of holes, no? So same size of holes represents what? Area of the orifice is constant in both of them. So rate of diffusion, already we have written it is A into P divided by root D, no? Clear? So area is same. And one more point which I understand is equal number of moles, he said. So pressure is also a constant. So therefore I can write pressure is also a constant. Okay. Then if you make the same size of holes, which balloon will contract first? Can you say? Which balloon will contract first? Contracting means small size. Which balloon's size will become smaller? So the balloon which loses more gas, that will contract first. So which balloon will lose more gas? So these two are constants, no? So R is proportional to 1 by root D. Okay, ma? And density, molecular weight, they are constant. So 1 by root 1 by M. This is what I have to write. Clear, no? So therefore, rate of diffusion R1 by R2 is equals to square root of M2 divided by M1. This is how I am comparing two gases, no? Definitely I can write like this. Okay. So rate of diffusion of which gas? Hydrogen gas divided by rate of diffusion of helium gas is equals to square root of molecular weight of helium gas divided by molecular weight of hydrogen gas. So what is the molecular weight of helium gas, ma? Helium 4. So therefore I will write 4 divided by hydrogen gas 2. So 4 divided by root 2. Clear, no, ma? So therefore RH2 is equals to root 2 times of RHE. This is what I have to write now. Okay. So the rate of diffusion of hydrogen, it is root 2 times greater when compared to the rate of diffusion of helium. So which gas diffuses fast? Definitely hydrogen. Its rate of diffusion is greater, no? Root 2 means 1.414. It means 41% greater rate of diffusion is present for hydrogen when compared to helium. So when you make same size holes, so hydrogen gas escapes very fast when compared to helium. So hydrogen balloon also will become very, very, very smaller when compared to helium balloon. Okay. So therefore what I say, rate of diffusion of hydrogen is greater than rate of diffusion of helium. Therefore H2 balloon contracts fast. Contracts faster when compared to helium balloon. That's all. Okay, ma? So this is the question. So a bottle of dry NH3 and a bottle of dry HCl, clear, ma? They are connected to a long tube and they are opened simultaneously. Okay, ma? So the white ring means what? See, my NH3 and HCl, when they react with each other, then NH4Cl will form, no? So this is white in color. So white ring formed, it will be closer to what? That is, will it be closer to NH3 or will it be closer to HCl? That is the question. Okay. So consider these are two boxes. Okay, ma? And here I have NH3 and here I have HCl. So both of them, they are connected by a tube. Clear? And both the tubes, they are opened. Okay, ma? Then a white ring will be formed, and the white ring is definitely NH4Cl. It means, so from this cylinder, NH3 starts diffusing, no? And from HCl cylinder, HCl starts diffusing. So both of them, after reaching somewhere, they react with each other. Okay? And wherever they react, a ring will be formed. So this ring will be formed, will be closer to NH3 or closer to HCl. How can you say? So everything depends on what? Everything depends upon molecular masses only, no ma? So therefore what I say, therefore rate of diffusion is directly proportional to 1 by root m. Okay, ma? See ma, here he did not say anything about mass, anything he did not say about mole fraction, anything he did not say about number of moles. It means we have to consider pressure to be constant. Are you able to understand? So this is very important point. So make a note of that point. So note point of what? Okay. Anything about MTG. Okay, ma? So anything about moles, mole fraction, weight, nothing is given. Is not given. Okay, ma? Then consider, what we have to consider? Then consider pressure is a constant. So in both of them, we assume that same amount of pressure is present. Okay, ma? If he said anything about that, then we should have taken that one into consideration. He did not give anything of a number of moles, no? So in such situations, you have to take pressure to be constant. Okay. Now, what is the molecular mass of HCl? Okay, ma? Hydrogen is 1, so chlorine is 35.5, so total 36.5 grams. For 1 mole, this is the molecular mass, 36.5 grams. Similarly, which is the another one, ma? NH3. Okay. Nitrogen, 14 plus 3, how much? 70. Okay. So therefore, which mass is greater when compared to which mass? Definitely, the mass of HCl is larger when compared to NH3. Clear, no, ma? So, which gas will diffuse very fast? NH3 diffuses very fast. Why? Molecular mass is very less, no? If molecular mass is very less, rate of diffusion will be very fast. Clear, no? So, this gas, it travels, it diffuses very fast. And HCl will diffuse very slow because its molecular mass is bigger. Okay, ma? So, therefore, where this white ring will be formed, ma? White ring will be formed very close to HCl. Are you able to understand? That's our answer. Okay. So therefore what we write as molecular mass of HCl is greater, it diffuses slowly. It diffuses slowly. Therefore a ring is formed. Ring is formed closer to HCl. That is the condition. Clear? That's all. Okay, ma? So this is the next question. So 0.5 moles each of hydrogen, sulfur dioxide and CH4, they are kept in a container. Are you able to understand, ma? So a hole was made in the container. So it means all of these gases, they are present in the same container. Okay? Previously we have taken different containers, no? But here all the gases, they are present in same container. And every gas is of 0.5 moles only. What do you understand? Pressure is a constant. It means every gas will exert same pressure on the walls of the container. Are you able to, because number of moles they are same. So therefore what we write, first observation is number of moles are same. Number of moles are same, is same. Grammar ఒకసారి గుర్తు తెచ్చుకోండి.
Moles కాదు సార్.
But we are measuring to number, no? But we have different gases, no? Number of moles is same. I think that is correct. Okay, ma? So therefore, they are kept in a single container. So therefore, what I can say, therefore, pressure is a constant. So every gas is exerting same pressure on the walls of the container. So if pressure is same and the hole is also same for all of them, no ma? So therefore, area of orifice is also a constant. And after 3 hours, so time taken is also constant. Clear? Then in that condition, rate of diffusion is inversely proportional to root m. Okay? So which gas has highest molecular mass, that gas will diffuse very slow. Okay? Now let us calculate molecular masses of each of them. So molecular mass of hydrogen is how much? So it is 2. Molecular mass of sulfur dioxide is how much, ma? 16 plus 16, 32 plus 32, 64. Clear, no, ma? So molecular mass of CH4. So 4 plus 12, 16. Okay, ma? These are the molecular masses. Understood, no? 2 grams, 64 grams and 16 grams. So therefore, which is having least molecular mass, ma? Hydrogen. So this gas will diffuse very fast. Hydrogen will diffuse very fast. And next followed by CH4, next followed by SO2. So after 3 hours, which gas would have gone by a very large quantity? H2 would have gone by a large quantity. Next followed by CH4, next followed by SO2. So which gas is present in more number of molecules in the container? SO2 is present in more number because it is not diffusing very fast. No? Okay, ma? So for this gas, if 10 molecules are escaping, for this one 4 molecules are escaping, and for this one only 1 molecule is escaping. Clear, no? So the number of molecules of SO2, they are very large, which are present inside the container. I am not discussing about escaped molecules. I am discussing about those molecules which are present inside the container. So inside the container, more number of SO2 molecules are present. No? So automatically pressure given by SO2 will be greater. Okay? Because more hydrogen molecules will escape, followed by CH4, then followed by SO2. So therefore what I write? Therefore I write more number of ఆశిష్ ఐపీ చదివి బ్రెయిన్ పనిచేయటం లేదు కదా, కరెక్టే కదా, అర్థమైంది నాకు విషయం. సో మోర్ నంబర్ ఆఫ్ H2 విల్ ఎస్కేప్ కంపేర్డ్ టు CH4 and SO2. Okay, ma? Therefore in the container more number of SO2 molecules are present, followed by whom? Followed by CH4, and again followed by finally whom? Followed by H2. Clear? Therefore, partial pressure of sulfur dioxide is greater than partial pressure of CH4 is greater than partial pressure of H2. Clear? Understood now? So, that gas which has more number of molecules, it will show greater pressure, because already we discussed that pressure is directly proportional to number of moles or number of molecules of a gas. No? Which gas is escaping by large quantity? Hydrogen. So finally its pressure will be very less after 3 hours, because only less hydrogen molecules are present, but more SO2 are present. So pressure of SO2 will be greater. That's it. But initially pressure was constant. This is the point which you should understand. Before making a hole, pressure given by every gas was same. But after 3 hours, pressure given by each gas will be different. That's it. Okay, ma? Okay. So let us see this question. Ma? So 4:1 molar mixture of helium and CH4. Okay, ma? is contained in a vessel at 20 bar pressure. Okay? So due to hole in the vessel, the gas mixture leaks out. What is the composition of the mixture diffusing out initially? Okay? So first let us see what are the values which are given. Molar mixture is given, Nama. So it means number of moles of helium divided by number of moles of methane gas. They are 4:1. This is the first data which is given. Okay? So same relation, I can write the pressure of helium divided by pressure of CH4 also. No? This is the first information you should write down. Because already we discussed that. What is the ratio of moles? Same is the ratio of pressures also. If number of moles increases, pressure also increases. First information which you should get. Otherwise you cannot get the answer. Understood, no? So therefore definitely pressure is a variable, no? Pressure, is it a constant? No. Pressure of helium, it is 4 times greater when compared to pressure of methane gas. Understood, no? Therefore what I can say, therefore pressure is a variable. It is not a constant. Okay? So hole is made, so gas leaks out. So time of leaking of gas is same for both the gases, no? Because from same hole, both the gases, they are leaking out. So therefore times taken also they are same. So therefore this is the question based on number of moles of a gas and pressure of the gas. Therefore how can I write a relation? N1 by N2 rate of diffusion. R1 by R2 is equals to, I can write. Already we have written an equation, Nama. So N1 by T1 multiplied by T2 divided by N2 multiplied by square root of M2 divided by M1 multiplied by P1 by P2. This is what I have to write now. Clear, Nama? Additionally, I have written P1 by P2 also. Why? Pressure is a variable. So definitely rate of diffusion is directly proportional to pressure. Okay? So time and time will get cancelled. Now just substitute all of them. That is our answer. Clear, Nama? So first of all, let us take a rate of diffusion of helium divided by rate of diffusion of CH4 is equals to N1. What is the number of moles of helium? 4:1 ratio multiplied by square root of, what is the molecular mass of CH4? 16. Molecular mass of hydrogen? Helium? Helium 4. Okay. So multiplied by P1 by P2. Same as that of N1 by N2. Because already we have discussed that concept, no? So again now 4 divided by 1. So do the calculation. So 4 by 1 multiplied by 4 by 1 multiplied by how much? How much is this one? 4, 2. 4, 2. This is what I will get now. But I am getting a different answer. Helium. So I am writing a square root of CH4 by helium. Helium 4 only, Nama. Atomic number is 2, molecular mass is 4. Helium. Helium single atom only, no? Inert gas, Nama, it never reacts with another. Helium, atomic number 2, Nama, mass number 4. Correct only. But what is the value I am getting? Number of moles 4:1. Pressure 4:1. Everything is correct only, no? So therefore what is the ratio I am getting? 32:1. I am getting, is it? Maybe 32:1. Let us check the answer. Okay, ma? So here N1 by N2 is equals to P1 divided by P2. This is equals to 4 by 1. Clear? Therefore the equations are rate of diffusion R1 by R2 is equals to N1 by T1 multiplied by T2 divided by M2 is equal to square root of M2 divided by M1. And here pressure is a variable, Nama, so I will write P1 divided by P2. So this is the additional equation. Okay? So if pressure is not a variable, definitely no need of P1 by P2. But here number of moles are different, no? So pressure also will vary. Okay? Now just do this calculation. So therefore R1 by R2 is equals to times of gas diffusing is same, no? T means time here. Number of moles are how much? R by 4:1. is equals to square root of 16 by 4 multiplied by pressures are 4 by 1. Clear, Nama? Therefore, what is its calculation? How much, ma? So here also I have to multiply by P1 by P2, ma. On both sides I have to multiply, no? So therefore, what is the calculation I am getting? 4, 2. So 2 into 4 divided by 1, this is equal to 8:1. Okay? ఇక్కడ 2 వస్తుంది కదరా, 4 2 8 కదా. ఈ పక్క కొంచెం వేరీ అవుతుంది, అదే ఏమవుతుందని చూస్తూ ఉన్నా. సో నౌ వీ విల్ స్టడీ అబౌట్ real gas equation. Until now we have been studying about ideal gases. Now we are going to study about real gas. Okay, so for example, if you take this one, this is the equation of an ideal gas. Okay, ma? PV is equal to nRT. Okay, and how many ideal gases are there? Practically there are no ideal gases, but if temperatures are very high and if pressures are very low, then normal gases also they behave like ideal gases. So therefore, for ideal gas, this is the equation. PV is equal to nRT. So if I write this relation, PV divided by nRT, then it is equal to 1. Are you able to understand, ma? And this PV divided by nRT, this is called as Z, which is called as compressibility factor. Okay, ma? So this Z is called as compressibility factor. So if this Z, if it is, we can have two conditions here. So if Z is equal to 1, okay, ma, then the gas is an ideal gas. Okay, and when Z is not equal to 1, then it is a real gas. Is it clear, ma? So if Z is equal to 1, definitely I can call it as an ideal gas. But if Z value is not equal to 1, that is Z value may be greater than 1 or Z value may be less than 1, then in that condition, that gas I can call it as a real gas. Okay. So if Z value is greater than 1, are you able to understand? Then it means that, okay, ma, PV divided by nRT, it is also greater than 1. Z value is greater than 1, PV divided by nRT is also greater than 1. But here nRT, it is a constant, it is not varying, only PV is variable in this condition. So if PV divided by nRT, if it is greater than 1 and nRT is a constant, then it also means that PV is greater than 1. This is what I can write. Okay, ma? So it means PV is greater. So therefore I can say PV is greater, it is larger. So if PV is greater, definitely I can say that in this condition, okay, ma, molar volume, it is definitely greater than 22.4 liters at STP. Okay, ma? What is meant by molar volume? Volume of 1 mole of a gas. Clear? So at STP, any ideal gas, it will occupy 22.4 liters of gas. 4 liters of volume. But in this condition, if Z is greater than 1, it means PV is greater, then I can say molar volume is definitely greater than 22.4 liters at standard temperature and pressure. Okay, ma? Whereas ideal gas exactly occupies 22.4 liters only. Okay, so therefore, if volume is greater, then also I can say that repulsive forces are dominant. This is what I can say. Okay, ma? So if repulsive forces are dominant, then only volume will be greater than 22.4 liters. Okay. See, in ideal gases, we considered that there are no what you call attractive forces, there are no repulsive forces. Okay. But for real gases, definitely there will be attractive forces also, there will be repulsive forces also. But sometimes repulsive forces will be dominating, sometimes attractive forces will be dominating. So in this condition, repulsive forces are dominant. Clear, no? Similarly, exactly opposite condition, how I can write if Z value is less than 1, definitely I can say PV divided by nRT is less than 1. Clear, Nama? And nRT is a constant, so therefore I can say that PV is smaller. If a PV is smaller, I can say that molar molar volume is less than 22.4 liters at standard temperature and pressure. Okay, ma? It means volume is reducing in this condition. If volume is reducing, it also means that repulsive forces are not dominant, but we can say attractive forces are dominant. Attractive forces are dominant in this condition. This is what I can write. Okay, so this is a small discussion on Z value, which is called as compressibility factor. Okay, make a note up to here. Okay, ma? So then we study about the equation of a real gas, which was given by van der Waals. So therefore it is called as van der Waals equation of a real gas. Okay, ma? So this equation is written like this. So P plus n square V divided by A square multiplied by V minus NB is equal to nRT. Okay, ma? For how many moles of gas? For n moles of a gas. Clear? Similarly, for 1 mole of a gas, how can I write? I can write P plus V by A square. Okay, ma? So n square A by V square, ma. Okay? So P plus A divided by V square multiplied by V minus B is equals to nRT. For how many moles of gas? For 1 mole of a gas. This is how I can write. Clear, no? Then what is this A by V square? This is called as correction in pressure. Correction in pressure. And B is called as correction in volume. Okay, ma? So what is the reason that we are writing a correction factor for pressure? Reason is that, okay, ma? In real gases, there will be forces of attraction or forces of repulsion. So these forces, they tend to change the actual pressure which molecules should exert on the walls of the container if it is an ideal gas. Are you able to understand? So therefore, definitely pressure changes because of intermolecular forces. Okay. And similarly, what is the reason for we are writing a correction factor or correction term in terms of volume also? Okay. So in ideal gases, we assume that the molecules, they are having negligible size and negligible volume. Okay, ma? But actually, if a container is very small or if number of molecules, if they are very large, then definitely volume of the molecules also we have to consider. So therefore, the empty space is given by V minus B, where that empty space is the total volume of the container, and from that we are removing the volume of the molecules which are present. Okay, so therefore a correction term means pressure is also present, a correction term in volume also we have to write down. Okay, now in this equation, what does A represent? Okay, ma? What does this A represent? A represents force. Okay, ma? And force may be force of attraction also, or it may be force of repulsion also. But generally we take force of attraction. Generally we take force of attraction. Okay, ma? So generally force of attraction is considered because maximum force of attraction will be present between the molecules. Okay. So therefore also we can say that A is directly proportional to liquefaction of a gas. Okay, ma? It means if A value is greater, it means that that gas can be easily liquefied. How can you say that gas is easily liquefied? Because A is directly proportional to attraction. If attraction between the molecules is greater, then gas can be easily liquefied also. Clear? Similarly, what is meant by B here? Okay, ma? B is called as correction in volume. Okay. So therefore, B can be written as 4 multiplied by 4 by 3 pi r cube multiplied by Na for 1 mole of a gas. Okay, ma? Okay. Where 4 by 3 pi r cube is the volume of single atom or single molecule. Okay. And how many molecules are there? Na number of molecules will be present for 1 mole of a gas. And that I have to multiply by 4. Because this is how we derive the B value. So there is some derivation which we are not doing. So just you remember them. For example, if you say this is a molecule surrounded by many molecules, are you able to understand, ma? So consider this total volume. Then we have many empty spaces which are present here. Okay, ma? So all those empty spaces I can get only if I do this type of calculation. So B is equals to 4 into 4 by 3 pi r cube multiplied by Na. Where this 4 by 3 pi r cube is called as volume of single molecule. That is the formula. Okay. So what does B represents? B represents size of a molecule. Okay, ma? If B value is greater, it means size of that particular molecule is also greater. Okay. For example, if you write B value of oxygen is definitely less than B value of ozone. Clear? Because ozone is a bigger molecule when compared to O2 molecule. Okay. So that is what is represented by B here. So A represent forces, which is responsible for change in pressure. B represents the correction in volume, and volume is because of volume of the gas molecules. Clear now? In real gases, volume of the gas molecules is negligible, we don't consider. But in real gases, and when volume of the container is very small, or number of molecules, gas molecules, if they are very large, then the size of the molecules also we have to consider. So therefore, correction term is B depending on volume of the gas molecules. Okay, ma? So this equation is called as the van der Waals equation for real gases. Okay. So make a note up to here. We will have some cases related to this one. Okay. Okay, ma? Now let us see what are the different cases we can study in the case of this real gas of van der Waals. Okay. Now let us see. Okay, ma? So first case which we study is if pressure is very low. Okay, ma? Pressure is very low pressure. If pressure is very low, then volume should be very large because nRT is a constant, no, ma? Because nRT is a constant, if pressure is very low, volume should be very large. Okay, so therefore I can say volume is large. Okay. If volume is very large, so definitely you can remove this correction term here, okay? Because generally correction term will be very small, no, ma? So if V is very large, B will be very small, so you can remove the correction term there. So therefore what I can write P plus A by V square multiplied by V is equal to RT. Okay, so we are removing the correction term in the case of volume. Now we will multiply this, so PV can be written as A by V is equal to RT. So divide everything by RT, so PV divided by RT plus A divided by V RT is equal to 1, and PV by RT is called Z compressibility factor, so Z is equals to 1 minus A by V RT. So this is the equation which I got. Clear, na, ma? And by looking at this equation, definitely I can say that Z value is less than 1. Okay, ma? So here I can say that Z value is less than 1. So if Z value is less than 1, what is happening here? So definitely PV also will be lesser. So therefore I can say that volume reduces, and therefore here attractive forces are dominant. Attractive forces are dominant in this condition. Clear, no, ma? So next we take one more condition. Second condition is if volume is very less. Okay, ma? If volume is very less, it means pressure is very large. So if pressure is very large, you can remove the correction term which is present. So therefore I will write P multiplied by V minus B is equal to nRT. Clear, na, ma? So therefore PV minus PB is equal to nRT. So therefore PV divided by nRT minus PB divided by nRT. Okay, ma? So this is equal to 1. This is the relation which I can write. Are you able to understand? Okay. So number of moles is 1 only, no need of writing nRT here. Just you can write RT in this condition. Okay. So therefore PV by RT is nothing but what? It is nothing but Z. So Z minus PB divided by RT. So this is equals to 1. So therefore what is Z value? Z value is equals to 1 plus PB divided by RT. Are you able to understand? So this is the equation which we got. Now by looking at this equation, I can say that Z is definitely greater than 1 because here we have 1 plus PB by RT, no? Clear, no, ma? It means definitely Z value is greater than 1. Okay, ma? So if Z value is greater than 1, it means which forces are dominant here? I can definitely say that repulsive forces are dominant in this condition. Okay, ma? So repulsive forces are more dominant in this condition. Okay. Similarly, I can study one more case. Ma. One more case is that pressure is less and temperature is very large. Okay. So this is a condition. So I hope you remember this condition. Ma. This is a condition where any gas behaves like an ideal gas. Okay. So therefore pressure is less and temperature is very large. Okay. See, if temperature is very large, Okay, if temperature is very large, then what I can say, the gas molecules, they have very high velocity. Their kinetic energy will be very large, their velocity will be very large. Okay, and if velocity is very large, so the attractive forces and repulsive forces, they play a very small role. Almost they play no role. So therefore, you need not write the correction term in the case of pressure. So what is the reason for writing the correction term in the case of pressure? Only attractive forces and repulsive forces were responsible. Okay. So therefore I can say if temperature is very large, okay, then forces does not play any role here. Okay. So therefore I can write, you can remove the correction term in pressure. Remove correction in pressure. Okay, ma? Similarly, we are also saying that pressure is very less. Pressure can be very less only when volume is very large. Okay. So therefore, again, you can remove the correction term in the case of volume. Okay. If you remove the correction term in the case of volume, then what is the equation I will get? I will get PV is equals to nRT. This is the equation which I guess, and this is definitely the equation of an ideal gas. Okay, ma? So all these conditions you are supposed to remember very carefully, ma, because previously many questions were asked on these concepts in previous NEET and MAINS examinations. Okay, make a note. Okay. So the next concept in states of matter is kinetic theory of gases. Okay, so listen very carefully. See, for example, if you take a gas container, so this is a container which is filled with gas. Okay, and consider here there is a piston which is enclosing this gas. So these are the gas particles which are present inside this container. Okay, so these gas particles, they will be a continuous random motion will be present in them. Continuously, these molecules, they will be moving. Okay, so they will collide with the walls of the container and they will be returning back. So continuously, they will be moving in random motion after collisions. Are you able to understand? So for movement, they require energy, no ma? If molecules or atoms in the container, if they are moving, it means they have some kinetic energy. So from where these atoms got this kinetic energy? Can you say? From where these particles got this kinetic energy? Even the atoms and molecules of air also, continuously they are in motion, no ma? So who gave this energy? Atmosphere. Atmosphere gave this energy, no? So what is the temperature of the atmosphere? Some 30 to 40 degrees Celsius. So by taking that temperature, these molecules, they will have some kinetic energy. Are you able to understand, ma? And that kinetic energy of each molecule or each atom, anything you can say, this is equals to 3 by 2 kT. This is a formula. Okay, ma? So kinetic energy for each molecule is how much? It is 3 by 2 kT if I consider these gases to be ideal gases. Are you able to understand? So if I want to calculate kinetic energy for 1 mole of molecules, then can you say how can I change this equation? And what is meant by K? Already we have written, K is called as Boltzmann constant. K is called what? Boltzmann constant. Are you able to understand? Okay. Now, this is the kinetic energy of single molecule or single atom for a ideal gas. Okay. Now, if I want to calculate kinetic energy for 1 mole of molecules, then how can I change this equation? Anybody, can you say? Into Avogadro number, that's it. Clear, Nama? So 3 by 2 kT multiplied by N into A, that's all, no? So this is the energy of single molecule. In 1 mole, how many molecules will be there? Avogadro number of molecules will be there. So multiply by Avogadro number, you will get kinetic energy for 1 mole of molecules. That's all, Nama? And already we have studied that K is equals to R by NA, Nama? K is equals to R by NA. Okay. So therefore, R can be written as K into NA, no? And here I have that K and NA, no? So instead of K and NA, what I can write? I can write R. So therefore, it is 3 by 2 RT. Now, what is meant by 3 by 2 RT? This is the kinetic energy for 1 mole of gas or 1 mole of atoms or 1 mole of molecules. Are able to understand how we are deriving? Similarly, how can I calculate kinetic energy of 2 moles of gas? Can you say? For 1 mole, this is the kinetic energy. If I want for 2 moles, into 2, that's all. So therefore, I can write it as 2 into 3 by 2 RT. This is how I can write, Nama. Similarly, kinetic energy for n moles. How can I calculate? or I will write small n. Kinetic energy for n moles. N into 3 by 2 RT. This is what I can write now. So therefore it is equals to 3 by 2 n RT. Okay, ma? So this is the kinetic energy of n moles of a gas. Understood now? Clear now? So this is a small discussion on kinetic energy of gas. Clear? Where ma? Definitely we can write. 3 by 2 nRT is there, no? Instead of nRT you can write 3 by 2 PV also. That is also kinetic energy for n moles of a gas. Okay, ma? So definitely you can write kinetic energy of n moles of a gas. It is 3 by 2 into PV, pressure into volume. Because we have ideal gas equation, no, ma? PV is equal to nRT. Clear, no? So here already I have nRT, no? So instead of nRT you can write PV. This is one more equation. Definitely we can write. Okay? Okay, ma? Okay, ma? So next we study about the different kinds of velocities which we study in the case of kinetic theory of gases. Okay? So first velocity which we study is called as RMS velocity. What is meant by RMS? Root means square velocity. So VRMS. Okay, ma? RMS means what? Root mean square velocity. Okay? What is the meaning of this one? See, ma'am. So consider there are different molecules or atoms which are moving with velocities of V1, V2, V3, V4, okay, like this. So this is the velocity of different molecules which are present in a gas container, okay. Then I want to calculate the RMS velocity of all these gas molecules. How can I calculate? So in the name only it has no root. You take the mean of what? Of a square of the velocity of gas molecules. So therefore I will write VRMS is equals to square root of, okay, ma? So V1 square plus V2 square plus V3 square plus dash 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 Vn square divided by n. So this velocity is called as RMS velocity of a gas. Are you able to understand? So square, where is the square here? This is the square term, no, ma? This is the square term. Clear? Mean, we are taking average, no? So it is mean. And what is meant by root? We are taking this root, no, ma? So that is why this velocity is called as RMS velocity. Root means square velocity. Okay. And there are many other equations to calculate RMS velocity. Now, what are those equations? Let us write here. So VRMS can also be written as square root of 3RT divided by capital M. I can write like this also. This is one more formula. Are you able to understand? One more formula of RMS velocity. Similarly, we know that K is equals to R by NA, no, ma? So therefore, R value, how can I write? R value is K into NA. I can write like this. Are you able to understand? So if you take this relation and substitute here, VRMS is equals to square root of 3 into, instead of R, I can write K into NA into T divided by capital M. I can write like this. Okay, ma? So listen. So what is capital M here? Molar mass, mass of 1 mole of gas. Or you can call it as molecular weight, molecular mass of a gas. Clear? So therefore, VRMS can also be written as square root of 3KT divided by M divided by NA. Can I write like this? Okay, ma? So NA is in numerator, no? I am writing that one denominator to the denominator. Denominator to the denominator will become numerator only, no? But can you say what is M by NA, ma? M is the mass of 1 mole of gas molecules, no? So divided by NA? Mass of one gas molecule, that's all, no? Mass of Na gas molecules is capital M. So capital M divided by Na, you will get mass of one single molecule or one single atom. Understood, no, ma? So therefore, how can I write? I can write VRMS is equals to square root of 3KT divided by M naught. This is another equation. Understood, no, ma? And what is meant by M naught here? M naught is nothing but mass of single atom or molecule. Okay. This is called as M naught. Understood, no? Similarly, let us see one more equation. See this one. Okay. We have ideal gas equation, no? PV is equal to nRT. And what is capital M? Capital M is the mass of 1 mole of a gas. So therefore, number of moles are how many? Number of moles are 1. So therefore, PV is equals to RT, I can write, no, if n value is 1. So therefore, instead of RT, I can write PV also. So therefore, Vrms is equals to square root of 3 PV divided by m. So I can write like this also. Are you able to understand? Okay. Let us see one more equation. So Vrms can also be written as square root of 3P divided by m by V. I can write like this also. No? Mass divided by volume is called density. Density is mass by volume only, no? So therefore, what is the another relation I got? Vrms is equals to square root of 3P divided by D, density of the gas. What is meant by D? D is called as density of the gas. Okay. So these are some of the equations of RMS velocity of gas. Okay. And if you want, we can have one more velocity. Clear? So see, listen very carefully. Another relation. So kinetic energy is equals to half m Vrms square. This is how I write now. Velocities almost everywhere you will measure in RMS velocities only. Okay. Kinetic energy formula half mv square only, no? Velocity means which velocity? RMS velocity. Okay. So therefore, from here you will get one more equation, no? RMS velocity is equals to square root of 2 Ke divided by m. Or just you can write, if you write a small m, then it is the mass of single gas molecule. Are you able to understand? So therefore, it is equals to square root of, just I can write 2K divided by m naught. And m naught already we have written, no? Mass of single atom or single molecule. Okay. So these are the different formulae which we have in the case of what? RMS velocity of gas. Understood, no? And a question can be asked on any of these equations. So you should be very careful. Okay. In chemistry, you will find only 2 or 3 equations. I have given additional equations which are useful in physics also. Okay. So how many equations totally? Let us see. First equation. Where is the second one? Second equation. Okay, ma? What about this one? This one. Third equation. Okay, ma? What about this one? Fourth equation. Fifth equation. Okay. And this is the sixth equation. So totally 6 equations for RMS velocity of a gas. Okay. That's it. Okay. See, ma. So the next velocity which we study is, you can call it as average velocity. Okay, ma? So which is the next velocity we are going to study? Average velocity. Okay. Second one is V average. Average velocity of all gas molecules. Clear, no, ma? How can I calculate average velocity, ma? Consider this is V1, V2, V3. Like this Vn gas molecules are present. Then average, how can I calculate? V average is equals to just V1 plus V2 plus V3 plus dash 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 Vn divided by n. This is how I can calculate average velocity of gas molecules, no? Clear, no? You know how to take average, no? So here also same method of taking average. Addition of all velocities divided by number of gas molecules which are present, that will give the average velocity. Okay. And if I want to write it in the form of an equation, how can I write? Very simple. So in RMS velocity, wherever you find 3, okay, ma? Instead of 3, just you substitute 8 by pi. 8 by pi. Then that velocity converts into average velocity. Are you able to understand, ma? So make a note of that point. So what is the note point I have to write? Note point is that in RMS velocity equation, okay, ma? Instead of 3, we place what? We place 8 by pi. Okay, ma? Then all the equations, they will become equations of average velocity. Okay, let us see how we can change them. So here instead of 3, I will write 8 by pi. Then it converts into average velocity. Understood, no, ma? So here also instead of 3, I will substitute 8 by pi. Then the equation converts into average velocity. Clear? Then I go to this equation. So here also instead of 3, I will substitute 8 by pi. Okay, ma? Here also instead of 3, I will write 8 by pi. That's it. So these are my equations for average velocity. That's it. This is how you can remember. Are you able to understand, ma? So just wherever you find 3, just you substitute 8 by pi. So here also 8 by pi. Average. And you write all these total equations, ma. Average 8 by pi. Okay. That's it. Then all the equations of RMS velocity, they get converted into average velocity. Okay? Third velocity. Third velocity is called most probable velocity. Okay, ma? What is the name of third kind of velocity, ma? Third kind of velocity is called as most probable velocity. Okay? It is represented by VMP. MP means most probable velocity. It means what is the velocity which is maximum present in the case of gas molecules. Okay? For example, if I write gas molecules, they have velocities like this one. So consider one gas molecule is having a velocity of 1 unit. Second, another molecule 2 units, another molecule 2. Next 3, 3, 3. Okay, ma? 4, 4, 5, like this. Consider these are the velocities of different gas molecules. So out of them, which one is having high, which velocity is repeated many times, ma? 3 is repeated many times, no? So that 3 will be called as most probable velocity. The velocity which is repeated many times in the gas is called as most probable velocity. Are you able to understand? So write down. Okay, ma? So therefore, 3 will become most probable velocity because it is repeated many times. Okay, ma? Now, how to write it in the form of an equation? So let us write the note point. In RMS velocity equation, instead of 3, you substitute 2. Okay, ma? Instead of 3, we place 2. Then all the equations of RMS velocity, they will become the equations of most probable velocity. That's it. Okay, ma? So now just you replace 2. Here in average velocity, we have written 8 by pi, no, ma? Remove all the 8 by pi's and place 2. Then they will become the equations of most probable velocity. Okay, write down. So wherever you find 8 by pi, you substitute 2 RT by m. And this is MP. MP means most probable velocity. So here also I will write 2. And this is MP. MP. 2. Okay, ma? MP. 2. MP. 2. MP. 2. MP. 2. That's it. So these are all the equations of most probable velocity. Understood, Nama? So sometimes question will be asked on what is the relation between them. So very easily you can write relation between them, no? How can we write? Let us see. Okay. So relation between V RMS, V average and V most probable velocity. Clear, ma? So how can I write? V RMS is to V average is to V most probable. This is equals to square root of 3 is to square root of 8 by pi is to square root of 2. Can I write like this, ma? These are the terms which are varying, no? Remaining everything is same. Okay. So one point which I can see is definitely root 3 is bigger. Out of all of them, root 3 is bigger. Now let us see what about 8 by pi. Okay, ma? So 8 by pi means 8 by pi value 3.14. It is slightly greater than 2, no? So slightly it is greater than 2. Understood, no, ma? Greater than 2. So root 2 means greater than root 2, no, ma? So it means average velocity is bigger when compared to most probable velocity. So therefore, what is the relation? VRMS is the biggest, followed by V average and followed by most probable velocity. This is how I can write a relation between them. Understood, no, ma? That's it. Okay. Make a note. So this. No. See, ma. So this is the given ma. The RMS speed of hydrogen is root 7 times that of the RMS speed of nitrogen. Okay, ma? Then if T is the temperature of gases, then what is the relation between the temperature of hydrogen gas and temperature of nitrogen gas? Okay. So therefore, according to the given data, what he gave, ma? So RMS speed of hydrogen. So we will write V RMS of hydrogen is how many times bigger, ma? It is root 7 times of the RMS speed of nitrogen. This is what he gave, no? Okay, ma? So then I want relation between temperatures. It means you have to use, so I think 6 equations of RMS velocity we have studied, no, ma? So out of those 6 equations, you take any one equation where temperature is present. Okay, then very easily you can get the relation. So which relation I will use? Okay, ma? I can use square root of 3 kT divided by m naught. I can take this relation, no? Okay. Now can you say what is the meaning of this equation? I can take root 3 kT by m naught, or also I can take square root of 3 RT by capital M also. Are you able to understand? So what is the meaning of this one? I can also use square root of 3 RT by capital M also, no, ma? So what is the difference between this equation and this equation? This is, here m naught represents mass of single molecule. Here capital M represents mass of 1 mole of molecules. So anything you can use. Okay, so every molecule will have same speed, no? Every molecule will have a speed root 7 times when compared to the speed of nitrogen. So whether you take molar mass or single mass, anything is same. So I will take this one. Okay, so this is equals to root 7 times of RMS velocity of nitrogen. So 3 kT divided by again m naught. So this mass is for hydrogen, no, and this mass is for nitrogen. Clear, no? Clear? Similarly, here T means temperature of hydrogen, here T means temperature of nitrogen. Okay. Now see what are the terms which can get cancelled, ma? So 3k, root 3k will get cancelled, no? Then I will square on both sides. Square on both sides. Okay. If I square on both sides, what I will get? I will get 3h divided by mh is equal to root 7 and square will get cancelled, no? So 7 into Tn divided by mn. This is what I will get. Understood, no? Now what is the mass of hydrogen? Mass of single hydrogen molecule. So 2 atomic mass units. Clear, no? So therefore I will write here. So temperature of hydrogen divided by 2 is equals to 7 into temperature of nitrogen divided by, what is the mass of nitrogen molecule, ma? Nitrogen 28. Clear, no? So 7 1s are 7 4s are. So again 2 1s are 2 2s are. So therefore what I got the temperature of nitrogen is equals to 2 times the temperature of hydrogen. Okay. See if we have any such kind of answer. See now. Temperature of see whether our calculations are correct or not, ma? 7 4s are, 2 1s are, 2 2s are. So temperature of nitrogen is 2 times of temperature of hydrogen. Same answer I got. Okay. Let us check the options, ma? I think wrong options I have given. I think options I have given wrongly. Clear, ma? So you do one thing. So here you write down 1 by 2. Now it is correct, no? So temperature of hydrogen is half of temperature of nitrogen. So third option will be our answer. Okay? Make a note. Okay, ma? So next question is this one, ma? This was previous NEET question. So compressibility of the gas is less than unity at standard temperature and pressure. Therefore, what about the volume of this gas? Understood, no, ma? What is meant by compressibility factor? Already we have studied, no, ma? PV divided by nRT is equal to Z. Okay. So this is called as compressibility factor. Clear? So this value, it is less than 1. Then we have studied already that attraction forces are dominant. This is what we have studied, no, ma? Attractive forces are dominant. If attractive forces are dominant, then what happens to the volume of the gas? 1 molar volume will be less than 22.4 liters. Okay? At a standard temperature and pressure, 1 mole of any gas will occupy how much volume? 22.4 liters. But when attractive forces, when they are dominant, that volume will be less than 22.4 liters. So therefore, what is my answer? Option B. So Vm is less than 22.4 liter. Clear? Yeah. Okay. So this is the next question which is given. So Van der Waals equation, okay, of state for a non-ideal gas. It means real gas. Non-ideal gas is nothing but real gas. The term that accounts for intermolecular forces is dash. So Van der Waals equation is what? So P plus n square a by v square multiplied by v minus nb is equal to RT. This was the equation of van der Waals number. Clear, no? And this is for n moles of a gas. For how many moles? For n moles of a gas. For 1 mole of gas, Chapandi, P plus A divided by V square multiplied by V minus B is equals to RT. This is the equation for how many moles? For 1 mole of a gas. Okay. So here we have two correction factors. Number one correction factor is present for pressure and one correction factor is present for volume also. So which correction factor is related to intermolecular forces? Which one is related to intermolecular forces? A by V square is related to intermolecular forces. Already we have studied, no? So in ideal gas, there will not be any intermolecular forces. But in real gas, definitely intermolecular forces will be present. Forces can be either attractive or repulsive also. But in most of the time, it is attractive only. Are you able to understand? And because of the attractive forces, the net pressure of the gas on the container reduces. Okay. So therefore, because of intermolecular forces, what is changing? Volume is not changing, pressure is changing. Okay. So therefore, this is the correction term which is related to that accounts for intermolecular forces. So this is our answer. Understood, Nama? So therefore, if you forget, make a note here. Okay. So due to intermolecular forces, what is affected? Pressure is affected. Pressure is affected. Okay. So therefore, we have to write a correction term for pressure. That is. So previous NEET question, ma. So see this question. So for 3 different gases, values of van der Waals constants A and B, they are given. So where you find A, ma? A you will find in the correction term of pressure. Clear, no? And where you will find B? In the correction term of volume. Clear, no? So these values are given. Then which is the correct order of liquefaction of gases? It means that which gas will liquefy more easily? That's the question he is asking. So by looking at this A and B values, we have to say which of these options is correct. Anybody? How? Very good. That's the point which we have studied, Dama. So in van der Waals equation, P plus n square A by V square multiplied by V minus NB is equal to RT. This was the equation we have written, Dama. So B is called correction in volume, no? B is called what? Correction in volume. Okay. So, and what is A called? A is directly proportional to attractive forces and it is directly proportional to liquefaction of gas. This is what we have studied, Noma. It means more the A value, more will be the ability of the gas to liquefy. Then what is the purpose of B here? B is not useful for us. Just to confuse you, he gave these B values. There is no relation of B on liquefaction of gas. Just you have to check which value is having highest liquefaction. Y2 is having highest liquefaction, no? Then followed by Z2, then followed by X2. So wherever you find this option, that is my answer. Okay. 4.1 is bigger than 2.2, 2.2 is bigger than 1.3. So which option? Option Y2, Z2, X2. This is my answer. Are you able to understand, ma? That's all. Wow. Okay. See, ma. So this is the given question, ma. Van der Waals equation for CH4 at a low pressure. Okay. So it means that he is considering real gases only, ma. If we mentioned something about pressure or volume, it means he is saying about real gases instead of ideal gases. And what is the equation of a real gas? Okay, ma. P plus n square A by V square multiplied by V minus NB is equal to RT for n moles of a gas. But I think he gave a question on 1 mole of a gas, no, ma. N is not mentioned. So P plus A by V square multiplied by V minus NB is equals to R into T. This is the relation. Okay. So which one is lower, ma? Here pressure is lower. Pressure is lower, it means that volume is bigger, no? So therefore I write volume is large. If volume is large, what you have to do? You have to remove the correction term of volume. Because volume is very big, no, ma? So NB becomes very small. Are you able to understand? So whichever is bigger, so you remove the correction term of that particular parameter. Understood, no? Therefore, how can I write the equation? I will write P plus A by V square, okay, ma, multiplied by V is equal to RT. Okay. Now just manipulate this one and see out of these forms, which form you are going to get. So PV plus A by V is equals to RT. So anything which is matching, no? PV, this one is matching, no? So that is our answer. Okay. So PV is equals to RT minus A by V. So this was also previous APMT question. Okay.